Today, this workshop organized as a partnering with the WSO2. And our speakers are Professor Frank Lehman and Jonathan Bahan. So first of all, I would like to thank them for accepting the invitation and coming here to deliver a quite interesting workshop today. Let me briefly introduce these two resource persons to you. Professor Lehman is a full professor of computer science at University of Stuttgart, Germany. His research interests include software architect, high distributed applications, middleware, pattern language, and quantum computing. Frank is co-author over nearly 600 peer-reviewed papers with H-index 91, and he owns more than 70 patents. And he also kind of a writer of industry standards and elected member of Academia Europaea, fellow of several organizations and so on. At present, he works as a fellow at WSO2 as well. That's quite a short introduction. And for Professor Johanna, he's a senior researcher leading to the quantum computing and digital humanitarian research area at the Institute of Architecture of Application Systems of University of Stuttgart, Germany. His research lies in the intersection of computer science, media science, digital humanities, and quantum computing. It's quite interesting. It's digital humanities joined with the quantum computing. He also has a big profile to read, but I cut it short and would like to give these two gentlemen to start the workshop straight away. So our schedule is we do first few hours as you get tired, and then we will stop for refreshment, and refreshment will serve in the 5th floor, and then we can restart in 15 minutes and continue till evening, right? Okay, right. So as I said, we opened this workshop for university students, mainly in our university, plus other universities as well. So always we would welcome all of you to such kind of workshops which organized by UCSC in future as well. So let me give the stage to Frank.
So first motivation, why is quantum computing important these days? The first answer is because components on a chip get close to the size of an atom, right? At the end, you need to apply quantum effects in order to build computers. And certain domains like artificial intelligence, optimization require constant increase of compute power, right? Some manufacturers said, okay, we run out of compute power, and the only rescue in a very few years will be quantum computing, and quantum algorithms often show significant speed up or much higher precision and so on, or some operational advantages. I will cover some of them compared to classical algorithms. So what are the sample speed ups? Sample speed up is, for example, you can compute eigenvalues exponentially faster than classical algorithms. And computing eigenvalues is something absolutely important in many application areas that you know or might not know. For example, in feature engineering, right, you need to do principal component analysis. You build a matrix, then you compute the eigenvalues, and you can do that in polynomial time on a quantum computer. By the way, if you have questions, just interrupt me, right? Don't even hesitate, ask me, because if you have a question, very, very naturally your neighbor will have the same question. The downside is we will spend the time in the evening, right? If you ask too many questions, right? So factorization, we will also discuss about factorization, right? Splitting a number into prime numbers. You can do it with the polynomial algorithm. Classically, you only have exponential algorithms. I would explain a little bit about the downside because all of security will be done in a very few years. It's not decades apart, it's the best estimations is end of this decade, security as we know it is gone. The world will look very different. Next is molecule simulation, right? You can simulate quantum physical systems naturally on a quantum computer. This is used, for example, for individual medicine, right? Individual medicine is, why should the same medicine work for male and female, for me, for you. So we need to produce medicine that is geared towards our own body. You need a lot of compute power, and people already do that on quantum, begin that on quantum computers. So we are working with companies that are basically doing it. Right? By the way, the COVID medicine has not been invented, it's a computer artifact, right? So I always forget the name of the company. BioNTech. BioNTech has some vaccines. It's a computer product that did a lot of computation in order to compute a molecule that can help us to defend against COVID. Linear equation solving. So in I don't know what Pfizer did, I know what BioNTech did. It was again, it's a? Is BioNTech a different company? Yeah, BioNTech is a German company, Pfizer is a US company, right? But I think they also invested in BioNTech, yeah. Linear equations can be solved in polynomial algorithms, right? And it's used in machine learning everywhere. And so I could go on and on and on, but I'm stopping here. So use case, as I said before, machine learning, for example, implementing support vector machines, that's what Johanna will discuss tonight, this afternoon, sorry. Yeah, feature extraction, clustering, classification, with no applications in the area of fraud detection, recommender system, one of the famous movie streaming companies used quantum computers. So if you watch a certain movie and then you see others have watched the other movie, or you like this movie too, this is a recommender engine behind it. And there are implementations based on today's quantum computers. Outlier detection, optimization. This is one of the prime application areas of quantum computing already these days. You solve combinatorial problems like traveling salesman, minimum spending tree, max cut, that is used in scheduling, route planning, organizing power grids. You can simulate crashes, body stability of cars. So this is, you solve huge linear equation systems, and so on and so on. These is the application areas where quantum computer will be good, but can already be used on a small scale today. Right? I always try to point out what can be done today. So, in order to discuss quantum computing, I lead a little bit on quantum physics. So the heart of quantum physics is Heisenberg's uncertainty principle. It basically says if you try to measure the location of a particle and its speed, and delta is the precision, the more precise you want to measure the location of a particle versus the speed of the particle, it's always greater than a constant. That means you cannot measure both quantities, location and speed, with the same precision. Right? This is true for the atomic world, so you can't go to a policeman and say, no sir, you can't detect me, I haven't been here, either the location is correct or the speed is correct, don't argue. Because he's not a quantum physicist, right? He will say, no, okay. So this is at the heart of, so we are unsecure, right? The quantum world is inherently indeterministic. There is you can't be very precise here. And what is happening, this is my very famous experiment called Schrödinger's cat. Schrödinger is a Nobel Prize laureate in physics. He invented the thought experiment. The thought experiment says you have some radioactive material here, and radioactive material is decaying completely randomly, right? Absolutely stochastically. And there is a sensor, and the sensor has a lever here, and the lever holds a hammer, and under the hammer there is a glass bottle with very strong poison, and if stochastically, randomly, the atom is decaying, the sensor notes it, the lever is released, the hammer crashes, destroys the bottle, and then the poison is set free. It's a very cruel mechanism. And what Schrödinger did is he put a cat inside, right? And then he basically closed the box, and then I asked you, is the cat dead or alive? You say, I really don't know. because I don't know when this atom here will decay, right? If it decays once you close the box, of course the cat is immediately dead. But it may decay in 10 years, and the cat is alive. From the outside, the cat is both dead and alive, because you don't know what it is, right? It's a zombie cat, right? So that basically is, we say that the status of the cat is in superposition, some sort of overlay between the states dead and alive, right? In quantum physics, it has some mathematical background. You have here this angular brackets to indicate states. So the cat is in a superposition of two different states. And when I open the box, I know whether the cat is dead or alive. We hope that the cat is still alive. That means we measure, we observe what the outcome of my experiment is, and measurement destroys superposition. Because at the very moment when I open the box, I destroy superposition of being both dead and alive. I know now the cat is alive, and I'm glad, right? So superposition, we have a rough understanding of what superposition is, we have a rough understanding what measuring is, and we will discuss that at length. So superposition, mathematically, is the following. You have some states, like being dead or alive, and you build a linear combination out of it, and this is the actual state of a thing, right? Superposition, it's a linear combination, and strange as it is, nature allows complex numbers as the factors of the state vectors. So we are here in a complex vector space, not real vector space, you are in vector spaces over the complex numbers, right? It's called a Hilbert space, because if you have, so a finite dimensional space is a very nice space, and if you have an infinite dimensional vector space, you need to have an axiom of completeness. Every Cauchy sequence must converge, right? So an infinite dimensional vector space that is complete is called a Hilbert space, right? It's a state space. And measuring always reveals the result. If I measure, right, then I know what happens. That means the coefficients determine the probability that when I measure, I observe the thing in this state. That means we take the modulus of the complex numbers, square them. If we sum them up, it must be 1, because the square of the moduli is the probability in measuring the state phi I. Right? And because at the end I measure something, the probabilities sum up to 1. This is the Hilbert version. So the boss asks, how's your quantum computer prototype coming along? And Hilbert said, oh, great. And then the boss asked the project, he said the project exists in a simultaneous state of being both totally successful and not even started. The superposition. Can I observe it? That's a tricky question. Right? So this is, and there's yet another comic, right? According to quantum physics, these plates have been broken, but it will be shown even after the opening of the showcase, right? You must open it. So, and there are a bunch of postulates, quantum physics based on quantum mechanics, and there is a bunch of axioms behind it, the so-called von Neumann postulates. Every isolated physical system is associated with a Hilbert space, a vector space of the complex numbers, so-called state space of the system. First axiom. Next is, there's a special kind of operator. Operator is, in quantum mechanics, a linear map, right? So there is a linear map called an Hamiltonian operator that describes the development of a system in time that satisfies the following equation. So I have the system here, and if I want to find out how the system behaves over time, it's very easy. I need to find the Hamilton operator. It's a linear map times the vector that represents the actual state. So it's a partial differential equations, and all that you need to do is you invent a Hamilton operator that describes the evolution of a system in time. Right? This is very important. I will come back in 2 hours or so on that. And measuring is done by yet another operator called the observable on the state space. And what you measure is always an eigenvalue of this observable as a result of the measurement. I will come back to that all over again. And from linear algebra, we know the spectral theorem. You can write each and every Hermitian operator as this kind of a sum. Lambda is an eigenvalue, and p lambda is the projector onto the eigenspace. That means every linear map that is Hermitian, unitary, and so on can be written in this thing, right? And when you measure, so to speak, at the end you project the current state to the eigenvalue that you currently measure. So you get a value out of your measurement, which is lambda, and p lambda then takes the current state and projects it down to the eigenstate, and then the system evolves further on. And if you have a composite system, two different particles, for example, two qubits, as we will see, right? Then the system is the tensor product of the state space of the component system, not the Cartesian product, as you know from linear algebra. It's a tensor product. You get very fast, huge dimensions, which will become important because this is one of the origins of the power. You deal with very, very high dimensions and can do a lot of stuff that you can't do in classical computing. So typically, we have a 3-semester lecture. You need some math, and we give math. You need to understand what Hilbert spaces, Hermitian operators are, unitary, or blah, 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 blah. A lot of mathematics. I assume this is what you know, because you everyday work with it, right? So I skip that, and I avoid, of course, dealing deeper into this. So now we dive into quantum computing, because now we apply the quantum physics to information. Now I define what a qubit is. So meet the quantum bit. The quantum bit is true in state 1 and false in state 0 at the same time. That means it's in superposition of being true and false. That's a little shock. So a qubit is in the state false and true, and it's a linear combination, and alpha and beta are complex numbers, right? And the modulus squared is the probability when I measure the qubit to result in false, and modulus beta squared is the probability of measuring 1. And when I measure, I will either measure a true or a false. That means, as before, these squared moduli add up to 1. That basically means a qubit is a vector of length 1. That means it's a point on this unit sphere, right? So everything that happens, a qubit is a point on this unit sphere, but it's a little bit more complicated because the numbers, alpha and beta, are complex numbers. So they are not one-dimensional beasts, but they are two-dimensional things. And 2 plus 2 is 4. That means a qubit lives in a 4-dimensional real space, a 2-dimensional complex space. Can you imagine 4-dimensional things? Can you imagine? If you do, you may need to see a doctor, right? So, but luckily, you can introduce spherical coordinates, and then you measure. Then you can represent a qubit on the 2-dimensional unit sphere in 3-dimensional space, right? And this is called the Bloch sphere. And Bloch is yet another Nobel Prize laureate. And so we can represent a qubit as a point on this 2-dimensional sphere, right? So not too bad. This is what we can imagine. We will have tools that show you how a qubit will be modified when you apply a certain algorithm, right? There's tooling that graphically shows it to you. And we need this formula. That means if you have a qubit, right, any kind of qubit can be rewritten as cosinus. There is an angle theta, cosinus theta over 2, false, plus e to the power of I rho. This is a real number. This is a complex number. And theta is the angle between the qubit on the Bloch sphere and the z-axis. And if you project the qubit to the xy plane, then you have the angle rho between the x-axis and the projection. And these two angles, theta and rho, determine the state of a qubit on the Bloch sphere. Right? So this is easy. We started with a four-dimensional beast, complex numbers, alpha and beta, and at the end, if we want to represent the state of a qubit, two angles suffice to understand what the status of the qubit is. Right? And this is a 10-minute math. It's very simple to rewrite this other representation. What is the intuition behind a qubit? So classically, a bit is either true or false, 0 or 1. Right? It has two possible values, a bit, that we know. A qubit is a point on the Bloch sphere. These are infinitely many points. In fact, it's an uncountably many different possibility. Not two values, but an infinite number of possible values that the qubit has. Any point on the surface is a valid value of the qubit. Now, you manipulate the qubit, and how manipulation works will be discussed at length, right? You manipulate the qubit, and then you want to get the result of the algorithm that you applied to your qubit. This is then called measurement. So classical bits can be read. You can find the exact state being 0 or 1 of the qubit, but of the bit, of a classical bit, right? But you can't do that for a quantum bit because it's in superposition, and I measure 0 with this probability and 1 with this probability. And when you read a qubit, it must decide whether it is true or false. That means you destroy the superposition. So reading a quantum state destroys the current state. So the qubit is any point on this Bloch sphere, and when you measure it, it needs to decide for the North Pole, which is 0, or the South Pole, which is 1. Right? So reading destroys it, and measurement, to get the result of your quantum algorithm, is a pure random experiment. So quantum computing is all about random experiments, but clever random experiments. So we will find out that if you are a clever quantum physicist, right, you can influence the shape of the probability distribution to ensure that the correct result has been spit out. We will come to that. This is only the overview. So a single computation step means I have a qubit. A qubit is a vector of length 1 on the Bloch sphere, and a single computation step produces a new state, which is again a vector of length 1. That means here I have the qubit, then I manipulate it, right? And I get a new point on the Bloch sphere, and a length-preserving linear map is called a unitary map. You might have heard that in the past in linear algebra, right? In real vector spaces, it's called an orthogonal map, and here we speak about a unitary map in complex vector spaces. So a length, because a qubit, vector of length 1, is moved to another vector of length 1, it's a unitary map. That basically means a quantum algorithm is a composition of manipulating individual qubits. It means a composition of unitary maps, and the composition of unitary map is again a unitary map. So mathematically, a quantum algorithm is absolutely simple. It's any kind of a unitary matrix, right? And this then defines what a quantum circuit is. So any algorithm can be expressed as a series of manipulation of individual qubits, but be careful, I discussed in a couple of minutes another phenomenon called entanglement, which is the real miracle behind quantum computing, and manipulations out of 2 qubits. You can prove mathematically that any unitary matrix can be defined as unitary matrices in 1 dimension or in planes of dimension 2. You compose it and then you get any unitary map. It's some sort of normal form of unitary matrices. So you manipulate individual qubits, and this is then called a quantum circuit. Quantum circuit is typically drawn like this. We have the qubits, they are horizontal lines. Then you have the 1 qubit operators that are manipulated the individual qubits, and you have two operators that manipulate 2 qubits jointly. Here, these 2 qubits are manipulated, and these 2 qubits are manipulated. And we'll introduce this thing as a controlled NOT operation, right? You have an if-then-else operation, so to speak, in quantum. And this is basically it. So, and we use the shorthand notation like this one, right? This is the unitary on this bundle of qubits, And if you zoom inside it, what is the normal form of this unitary, you find out what kind of unitaries you need apply on individual qubits and which two qubits must be manipulated jointly. This is a quantum circuit. If you want to manipulate real-world data, customer data, blah, 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 right? They are not quantum states. You have classical data. How the hell do you get them into a quantum computer? Well, you need to analyze the classical data, and Johanna will discuss a little bit, right? Yeah, okay. Yeah, how you do it? So you generate a circuit that takes the quantum computer in a ground state, then you manipulate the ground state, and this circuit transforms classical data into a quantum state. It looks crazy, and I will explain you what this graphical notation means. So after this step, you have moved your classical data into a quantum computer because you produced a quantum state, and then the algorithm proper is running, right? Cracking keys and so on, right? Then your quantum algorithm produced a result. This is the resulting state of your algorithm, and now you need to get it out of the quantum computer. You measure it. Each qubit will be measured, and each qubit must decide according to its superposition, alphas and betas of the state, right? And in this case, you measure 0, 0, 0, for example. What you do is you draw a little diagram, a frequency diagram, and you say, okay, I measured 0, 0, 0 once. Right? I add a little bar there, 1. Then you repeat your experiment. Right? You have an iteration, and the next iteration, you observe this value. You take note in the diagram that you observed 0, 1, 1, 0, and then you run the circuit thousands of times. Typically, you start with about 1,000 shots. It's called a shot. Each iteration called a shot. So we do it now, and then what you see is you see probability, so to speak, piling up. Right? So you measure this diagram, and this is, without any doubt, a probability distribution. Right? So the result of your quantum algorithm is a probability distribution that next must be interpreted. Right? What is now the real result? We will discuss what that basically means, how you do it, right? So the result of a quantum computer is a probability distribution. There are a few examples, there are a few interesting algorithms that produce a concrete value, but often you result in the probability distribution. And then you need to post-process the result to get the classical result. What was the real result of it? And this mechanism has been invented by John von Neumann, who did not get a Nobel Prize, but in computer science he's famous. Everybody knows John von Neumann, right? That basically means a quantum algorithm. This is, if you read papers, a paper, the quantum physicists, they describe their algorithm proper, the unitary, and in fact what they do is they invent the Hamiltonian operators. They see a problem, they know Schrödinger equation, and they think about, I need to find a Hamiltonian operator that describes the behavior of an overall system, right? They invent the Hamiltonian. Then a mathematician knows that the exponential of a Hamiltonian is a unitary map. So the mathematician then computes the exponential of the Hamiltonian that the physicist did come up with. It's a unitary, and then the mathematician further computes the normal form of the unitary, which consists out of of manipulations of individual vectors and combined vectors, the quantum circuit. That means the first observation, a typical quantum computing project involves physicists, mathematicians, computer scientists, and domain experts. It's inherently a cross-domain project. So you can't sit down as a computer scientist and say, okay, I invent something new. You will fail. Either you are a genius. You understand physics in depth, mathematics in depth, and so on, right? So what we are doing is, Johanna and I, at our institute, we run a couple of huge projects. We always work with application companies, with physicists, with mathematicians, and so on. So this is what the quantum physicist comes up with. then we need to have classical preprocessing. We need to read data that I want to manipulate on a quantum computer, generate this state preparation circuit out of it. The state preparation runs, produces the quantum state that is manipulated by the algorithm proper. Then you perform measurement, you get a distribution, and you need to classically post-process the distribution to come up with a real result. That basically means that the quantum algorithm is always hybrid. If you speak to a quantum physicist, the physicist said, I invented a quantum algorithm. But this is, from an application perspective, completely wrong, because this is one piece of the quantum algorithm. As an applicant, I'm interested in processing my data and getting my result back. That means, an overall, if you solve a problem with a quantum computer, it's inherently hybrid. You need a classical computer and a quantum computer. That means the typical insight is quantum computers won't substitute current classical computers. A quantum computer is a specialized device. It can solve problems that can't be solved on a classical machine, right? It's a special kind of device with a completely new kind of processing paradigm, unitary matrices, right? But you need both, right? And here's now your first quantum algorithm. So I want an algorithm that results in 0 with probability 1/2 and in 1 with 1/2. So it's a random generator. So what we do is we initialize a qubit with false. False is very simple to generate in a quantum computer. It's called the ground state of the quantum computer. You initialize it with false. Then you use an operator, the Hadamard operator. I will explain that what it is. It's a manipulation that you need all over again in quantum computing on this initialized qubit. The value is stored in the qubit again. Then you measure x. And what happens here is, so this is the Hadamard operator. It's this matrix here. Now let's see. The Hadamard operator is applied to 0. This is pronounced cat 0. Cat 0 comes, if you have a scalar product, you have this left angular bracket, x, comma, y, right angular bracket. This is a bracket, a bra, and a cat. So the left part of a bracket is the cat, right? It's called cat. It has nothing to do with Schrödinger cat, it's only bracket, right? They ignore the C, right? Oh, this is the bracket. So, and this vector is in mathematics the first unit vector, 1, 0. Right? This cat corresponds to 1, 0, and the cat 1 corresponds to 0, 1. So if you multiply this, you get this thing here out, right? Then you get a superposition of 0 and 1. So the Hadamard operator is used to generate out of the ground state 0, the superposition of 0 and false, of true and false. Yeah? Then this algorithm, if I measure it, gets with 50% a 0, with 50% a 1. This is a perfect random generator, right? Classically, we computer scientists know that you can't produce real random numbers, only pseudo-random numbers, right? You can buy such a device for a couple of $100, right? You push a button, then you get a 1 or a 0. I have a colleague who is very proud to click on it and get a 0 or a 1. He paid a bunch of money for it. So this is what you can do, but it has in fact already applications, right? If you need to run stochastic experiments, it's absolutely fine to have real random numbers. There are algorithms that are impossible at all. The first shock is you can't copy qubits, right? Because copying would mean to take a look at the qubit, but if you take a look at the qubit, you destroy its state. It goes into 0 or 1, right? But it was before any point on the Bloch sphere. It's so-called no cloning theorem, right? You can prove it in 5 minutes. It's very, very simple. It was a shock to computer scientists. You can't clone qubits. That means you can't build quantum databases. Right? If you store data, and if you want to retrieve it, it's impossible. You can't copy it. You destroy the information there. Right? This is the first limitation. Persistent data that you can read is impossible. And there's a bunch of of no-go theorems, what you cannot do with qubits. And here's only one that I want to mention because we need next. So quantum register. A quantum register is a series of qubits, like a classical register is a series of bits. So I have my qubits here. I have n qubits. And what I have is the quantum register with n qubits is in superposition of the corresponding 2 to the power of n states. The qubits, so the ground states can be 0, right, the north poles. Then I have this state here, or the first one can be 1 and the others can be 0. This is this one here, and so on. So I have 2 to the power of n combinations of 0 and 1, and the quantum register is a superposition of it. Right? This sounds okay. Why does Frank mention it? Now it comes. So classical register with n bits still has only one value at a time. Right? The classical register, one value at a time. The quantum register has 2 to the power of n values at the same time. So if you have 50 qubits, it has 2 to the power of 50, which is 10 to the power of 15 in the area of peta number of states. If you have, then it is well known, if you have 100, this is a regular computer, you can access at IBM for free, you have 10 to the power of 30 states in parallel. And it is known that the atoms of the universe is less than 10 to the power of 90. That is, if you rewrite it, less than 2 to the power of 300. That means if you have 300 qubits, you have more states available than we have atoms in the universe. And what we are doing at our institute, we work with IBM machines that have 400 plus qubits, right? You cannot simulate it anymore. Because if you want to simulate this 2 to the power of 400 qubits, you need to turn each and every atom of the universe into a bit in order to simulate it, right? If you want to simulate quantum algorithms, we say that you cannot go beyond simulating 50 qubits, right? We have a high compute research center in Europe. They have more than 6,000 GPUs and they can simulate 45 or 46 qubits. And all 6,000 GPUs are busy, right? So 300, 400 that we are using here in practical application can't be simulated. And a single step in a quantum algorithm manipulates all this 2 to the power of n information at the same time. Right? You have a massive amount of information is manipulated in a single step. And this is called quantum parallelism. Right? Quantum parallelism is a huge power of a quantum computer, that you have tons of data that you manipulate in a single step of your quantum computer. And now we need to discuss, if I have 2 qubits, right, so the V, let's say that V and W are vector spaces over some field. We know that we have complex numbers. V has the basis V1 and Vn, W has the basis W1, Wm, and then we define the tensor product of the 2 vector spaces. It's not the Cartesian product. The tensor product produces an n times m dimensional vector space, while a Cartesian product, if you remember this, produces a n plus m dimensional vector spaces. And how is this vector spaces constructed? Algebraically, you create symbols, these kind of symbols, V1 tensor W1, V1 tensor W2, all these combinations, and this then forms the basis of a new vector space. This is the so-called tensor product of a vector space, and the quantum register is the tensor product of the vector spaces that represent a single qubit, right? That basically means a quantum register, so if the Hilbert space, the 2-dimensional Hilbert space of a single qubit, so this is a complex vector space that is spanned by 0 and 1. And if I have n qubits, I take the qubit vector space and tensor it n times, and then I get this is a new symbol, right? It's the vector space, the qubit vector space tensored n times, and the state has always the length 1 in this vector space, and this is in the state of the n-cubic quantum register. Some formalism. And the dimension of the vector space of n qubits is 2 to the power of n, which will become important in many applications. Johanna will discuss one in support vector machines, right? You can data that is cannot be linear separated in high dimensions. Let's take a brief look into hardware. What you see here is a superconducting chip with 5 qubits. You see here 1, 2, 3, 4, 5 qubits. These are microwave channels here between the qubits, because the qubits are manipulated by sending microwaves to them. Right? This is a superconducting one. In ion trap computers, you manipulate them with lasers. Right? It's hyper independent. You graphically depict a chip like this, and if you abstract any further, you draw a graph, and the lines between the nodes are the qubits, the lines between the qubit are these microwave connections, and if and only if there is a microwave connection between 2 qubits, you have a 2-qubit operator that can manipulate them. So these 2 qubits can't be manipulated at the same time because there is not a single connection between them. It's an art to build these kind of chips, because the more connections are on the chip, the more the connections disturb the state of a qubit. So this is a real engineering problem to design the structure, the topology of a chip. And here's what the quantum computer looks like. What you see here is, right, these are connections. Each of these tubes are connections through which you send microwaves to the quantum chip that is here, right? So this is a zoom over here, and if we zoom further, this is the quantum chip that you saw before. And the loops here in these connections where the microwaves are sent to is because you cool that down to 1,000 of the temperature of outer space, right? It's at 0.002 Kelvin. And if you cool it thus down, right, the material will be stretched, and if you don't have the curls in there, it will be destroyed. This is why they look so crazy, right? That you have the curls in this waves here, right? This looks very nice. So the design team in Italy that does the designs for Apple, they are also designing the computer that IBM has. And here you see a different kind of topologies of chips that IBM has publicly available that you can use if you get an ID, if you register yourself with IBM Quantum. This is a huge one. Right? You can, if you go to a tool that I show you in a couple of minutes, right, you can find out what the status of the CPU is. The color code means something, and here, for example, you see the connections. So these qubits, for example, can be manipulated jointly by a 2-qubit operator. These 2s can't, right? We will introduce another interesting computer science problem in a minute about that. This is a machine you don't have publicly available, you need to pay for it. Or if you are very kind to IBM and ask them and beg them on your knees, they will give you some credits that you can work with this kind of computer. These are 433 qubits. And the roadmap that will become important is that in 2029 they will have a couple of 1,000 qubits available, and here they have many thousand qubits available, and these are already, keep that in mind, logical qubits. That means error-corrected qubits. Qubits have errors as of today, which has some implications, and that basically means that either end of this decade, that many people say, or at least early 2030, security is gone, right? But the other this makes us nervous, but the other stuff is only beneficial. Individual medicine, right? Optimization problems that can be solved, and so on.
This is IBM supraconducting.
Speak up louder.
This is supraconducting quantum computing, like the processing qubits. It's not photonic or ions.
No, this is superconducting. These are superconducting chips.
The measurement doesn't change depending on the time of the algorithm.
there are vendors like IonQ. The question is this a roadmap of superconducting? Is the roadmap dependent on the technology that you use in order to build a quantum computer?
No, the measurement calculation, the measurement.
Measurement, yeah?
Yeah, the measurement.
Yeah.
Is it the same method, mathematical
No.
method?
No, the mathematics is always the same.
Okay. If it's
Always the
photonic
same.
or supraconducting,
So,
it will be the same. Okay.
from an algorithmic perspective, you don't care what is the underlying technology. But it turns out, I will mention it already now, certain kind of problems are better served by certain kind of hardware. So ion trap machines. Ion trap, you have an ion that are captured in a magnetic field, and they are manipulated by sending laser beams to the ion so that the ion that is captured in a magnetic field rotates. And an ion trap machine has an any-to-any connection. So each qubit can immediately couple with another one. You take a magnetic pipette and move the two atoms side by side, right? This can be done. They are very slow, but they have any-to-any connections. While a superconducting machine can't be built with any-to-any connection. And as a result, ion trap machines are very good for graph-based algorithms, like MaxCut and so on. And we use that, right? We have access to different kinds of hardware machines. While superconducting are excellent for optimization and so on. So at the end, if you run experiment, you find out it's a very subtle experience that you need to get, which kind of hardware to use. Right? At the end, I will come back to a huge environment that we have built in projects that give, it's a pattern-based system. We have patterns, which hardware to use for which kind of problem. But absolutely fine question, yeah? And this is here, Johanna and I, our first quantum computer, right? This is so that you get a feeling how tall it basically is, yeah? Yeah. Yeah. So. A photo? Yeah, no, I don't have a photo. I can go back. It's too dark. So this is the shell of the fridge. Within the fridge, you have this chandelier. They call it the chandelier. Oh wait, just a second. This is called the chandelier, right? And then you have, in fact, you have multiple fridges around this. One fridge cooling it down, cooling it down, cooling it down, and then you get this. Oh, sorry, this nice picture, and behind this black wall, there is a couple of ThinkPads, right? Regular machines. And these machines generate the microwaves. The machines generate the signals to the microwave in order to manipulate the qubits. And when you read it out, you have other connections. You send also microwaves to the qubits. Then they decay, they collapse, and send the microwave signal to the classical computer that transforms it into 0 or 1. Right? So there's communication going on between a classical computer that steers and controls the quantum computer. Welcome. So this is the single quantum computer. And if you want to have thousands of qubits available, right, this is a nice picture. Then you need bigger refrigerators, right? This is a former colleague of mine who runs this quantum stuff. This is the head of IBM. So they are building much bigger cooling devices to get a couple of hundred qubits in a single device. But however, you must plug these huge machines together in yet another arcade to get thousands and hundred thousands and millions of qubits that you have. So how do you determine now the result? Right? We spoke about measurement. We spoke about that measurement produces this kind of distributions here. And the final result, typically don't read the text, the final result is the result with the highest probability. So in most cases, the final result is to take a look at the probability distribution, and here the maximum is the result of your algorithm. There are other situations, I come to that. So basically it's an art of the quantum physicist to invent the Hamiltonian operator that shows that results in a quantum distribution that ensures, in a probability distribution, that ensures that the real result has a hopefully very high peak here. Right? It's also, I can't invent my own quantum algorithms because I don't understand enough physics. Right? So you really need a physicist who invents the algorithms and invents in such a way he has a gut feeling how to modify the Hamiltonian operator so that the resulting quantum probability distribution has a shape that makes it easy to determine the result of the quantum algorithm. We will come back to that when we discuss several algorithms. So we will discuss the algorithm of a Deutsch-Joscha. You always want to have this kind of a shape, because on the shape, and I will discuss the algorithm in a little bit detail, right? Based on the shape, you see what the result is. Another kind of algorithm, like the Grover algorithm, it's an unstructured search algorithm that is quadratically faster than the classical one, right? This produces these kind of a shape, so that the thing that you look, needle in a haystack, that has a very high probability. Right? So the shape of the distribution is important to define by quantum physicists. And now we come to the real fantastic thing. This is a state, and if I measure the first qubit, and the first qubit turns out to be 0, measurement means destroy superposition. I measure the first qubit, and only the information of the second qubit remains. If I measure a 0, the second qubit still has the chance to have a 0 or a 1, right? The first qubit is gone, right? And the second qubit remains in superposition of 0 and 1. And the reason why this is the case is because, this is a different one. If I measure a 0 here, right, then this whole state is gone. This summand is gone. Because I know I measure a 0, I'm in this part of the state space, and this is gone because here's no 0, here's a 1. That means if I measure a 0, I know immediately that the second qubit is also in 0. If I measure a 1 of the first qubit, this is gone because here's a 0. If I measure a 1, then the second qubit is in 1, 2. So when I measure here the first qubit, I immediately know what the state of the second qubit is. What's happening here? This is, by the way, called Einstein-Podolsky-Rosen paradox, EPR paradox. I'll comment on that in a minute. And the reason is, this state is what mathematicians call separable. I can rewrite this state as a tensor product of two independent vectors. This is a vector, tensor, and this is a vector on the second qubit. If you multiply it, you can use the tensor product as a multiplication. 0 tensor 0 is 0, 0. 0 tensor 1 is 0, 1. You can't do that in this thing. You can't rewrite this state as a tensor product of two independent states. And this is an example of an entangled state. An entangled state. So now I comment on this Einstein-Podolsky-Rosen paradox. You may know that Einstein got his Nobel Prize for quantum physics, not for general relativity. Although he is absolutely famous that he invented relativity theory, he got his Nobel Prize for quantum physics, because nobody thought that general relativity would have any impact on our life. And the Nobel Prize is given because you have impact on society. And Einstein soon didn't become a believer in quantum physics. He has a very famous quote saying, "God doesn't throw dice." So physics that is not deterministic, but is probabilistic, can't be the world that God creates. Right? Because we are all laws of physics, Newtonian physics, thermodynamics, everything is completely deterministic. You have equations and you know exactly, right, what happens after a certain amount of time. Quantum physics is completely different. It was always against Einstein's mind until he died. And in 1935, he published a paper together with Podolsky and Rosen, who at the sudden pointed out these kind of states are possible in quantum physics, and this can't be that the state of one particle, one thing, determines the state of the second thing because of the following. So what was his mental problem? The mental problem, not mental, how can I speak about mental problems of Albert Einstein? So the intuition behind is you have two qubits, the EPR state on the former slide. I have two qubits, and these two qubits can be entangled. Right? They can be entangled. I use this kind of graphics here. And what that means is as follows. So in an analogy, the two qubits are two dice. Right? And now I take the two dice, they are entangled, I keep one here, and one of you young guys fly to Mars. Right? Far away with your dice. When you arrive there after a couple of months, you say, I'm here, Frank. Then Frank throws his, and this goes for arbitrary distance, so the distance is lost there, right? You can even go to Andromeda galaxy or at the end of the universe. You are absolutely far apart. And then I take my dice and I roll it, and then I see the result, and immediately your dice shows the same result. Independent of any distance. But information can only be exchanged at the speed of light. This is general relativity. That means this phenomenon is in sharp contradiction to general relativity. And this is what Einstein buckled and said, this can't be. General relativity was at this point in time the most proven theory in physics. That tons of experiments have been entertained to prove that, and everybody knew general relativity is true. And now Einstein invented this thing and said, this contradicts general relativity, let's stop working on quantum physics because it must be wrong, because it violates general relativity. I would be glad to be able to tell you what the resolution is, but philosophers are still discussing it. There is no resolution. There are two different theories that are somehow in conflict. Right? We don't know what's going on in quantum physics, and it is after a few years ago there started something that's called it from qubit. It from qubit, basically, just as a second entanglement, it from qubit, what the theory is that explains quantum physics in compatibility with general relativity is extremely strange. It turns out that if you entangle, that each qubit results in a nanoscopic black hole. It's a nanoscopic black hole, right? Very small black holes. And when you entangle two black holes, they are connected by a wormhole. This is why I have drawn it here. So if you are science fiction fans, you heard about wormholes between space, and this is what this theory it from qubit says. It says you entangle a qubit is a nanoscopic black hole. You entangle them, and while you entangle them, there is a wormhole that got established between the two qubits. If you move them to different places in space, they are far apart, but the wormhole connects them. It's a bridge between the regular space that you have. That means they are very close together, although we think they are far apart. That means communication can take place over this wormhole in femtoseconds, in seconds that you can't measure. The last Nobel Prize has been granted because they could measure attoseconds. I don't know what atto really means, right? So, but this is a theory, right? It encompasses strange things like string theory, beat the hell out of me. It's a theory. People are pretty sure you will never be able to experimentally prove it, right? Because you need to measure durations that you can't measure. You can prove that you can't measure it. But this is a mental model that helps us to understand that quantum physics is somehow compatible with general relativity. So entanglement is an extreme powerful stuff. This is Einstein-Podolsky-Rosen. And entanglement is unique for quantum computing, right? There's no classical phenomenon that can simulate it, right? Only on a quantum computer is you can exploit entanglement. Right? And every computation that is not involving entanglement can be performed with the same efficiency classically in principle. Because if you have more than 45 up to 50 qubits, you can't simulate it anymore. But in theory, you can prove that if you don't use entanglement, in theory, you can use the same with the same efficiency classically. But again, in principle, because beyond 50 qubits, there's no chance to simulate it really. And there's a very famous theorem by Joscha and Linden. Every quantum algorithm showing exponential speedup compared to classical algorithms must exploit entanglement. Right? So entanglement is of utmost importance of quantum computing. And you will see in a quantum computer what you do very first, you bring your data in superposition, then you entangle the data, and then the real algorithm works. Right? And entanglement is used, only a very quick example, on quantum teleportation. So I talked about black holes and wormholes, and now I speak about Scotty, beam me up, right? So teleportation is the following problem. At location A, you have a certain qubit psi A, and you want to transmit only classical information to a location B, so that at location B, the qubit A can be reconstructed. This can be done. Although a qubit has an infinite number of potential values, right? It is suffice to send 2 classical bits to the recipient, and this suffice to reconstruct the qubit at B that has been constructed at A. So, but, a big but, A and B must agree in advance on an entangled 2-qubit state. So A and B must meet, entangle the 2 dice, right? A keeps 1 dice in the pocket, B went far away, right? And then A constructs a quantum state, right? No, and then A and B have their entangled qubits with them. A creates a new qubit, and A sends 2 qubits in an algorithm that I'm not going to explain here, how these two bits are generated, to B, and B can then recreate the qubit that A had there. Note that qubit B, that this qubit is gone away here because of the no cloning theorem. I can't copy a qubit. If A would still have this qubit here, this would violate the no cloning theorem. That means Scotty is here, right? It is beamed up, classical information is transported here, and then at the transmitter, at the recipient side, out of the classical information, my whole body is recreated. So far the theory. I would not be an object of an experiment here, but this is what you can do, right? And this requires, again, entanglement, not only in computation, but also in communication. And entanglement is also very important in quantum communication. And we need quantum communication to build a completely new infrastructure that is secure against attacks that want to crack our keys and so on. I may come to that. Should we have a 5-minute break so that you can stand up a little bit and relax a little bit? Or should I go ahead? Kasun, you need to tell me. I can go. Kasun, I can speak until tomorrow morning. Okay, so quantum operators. Absolutely. So Kasun said, Frank, go ahead for the next 2 hours. So we are now focusing on the algorithm proper, the unitary transformations here, right? So what are 1-qubit operators? Right? 1-qubit operator is a unitary map F that is manipulating an individual qubit. And the most important stuff is this matrix X, Y, Z. They are called the Pauli matrices. Yet another Nobel Prize laureate, right? These are manipulations. This is a quantum knot, right? You negate a certain qubit. This is a phase flip. I don't discuss the names, it takes longer. This is a Hadamard matrix that we already discussed. This is another very important matrix S, although it looks quite innocent. And this is a misnomer. It's called the P over 8 matrix, also, although here is P over 4. It's a misnomer. Right? It's used, somebody invented it, okay, bullshit. You draw them this way. A single qubit operator is a square on a qubit here. Here are the matrices, right? And here's an example. If I apply the X matrix to 0, this is the X matrix. 0 is this unit vector, 1, 0. If I multiply the matrix with the vector, I get this vector, and this is, what a surprise, the 1. That means X is a negation, right? The X matrix is a negation. And if I negate 1, you can multiply it, you get this set, you get a 0 out of it, right? So this is a negation. Hadamard produced a superposition. You start with 0, and then if you follow the computation, which I'm not doing here, right, you get this superposition out of it. So Hadamard creates out of a computer in ground state a computer in superposition. Now, linear algebra, maybe you recall that or not, you can not only build the exponential function with real numbers or complex numbers, also with matrices. Here's the matrix Y, and of course real number. You can take the matrix exponential, and if you compute it, you get this matrix out of it. That means the Pauli operators, X, Y, and Z, result in this kind of rotation matrices, right? This kind of rotation matrices. And now we have a geometric interpretation of this Pauli X, Y, Z matrices on the Bloch sphere. Here's the Bloch sphere, and the Pauli X operator, the matrix exponential of Pauli X operator, basically rotates the state theta, psi, into this state. It rotates on this, around this, by this angle around the x-axis. What a surprise! The Pauli Y operator rotates around the y-axis, and absolutely no surprise, the Pauli Z operator rotates around the z-axis. This, by the way, is the origin of the name X, Y, Z of these matrices, because the matrix exponential are describing rotation operators on the Bloch sphere, right? Pauli X, Y, Z. And a quantum computing vendor can't implement each and every unitary matrix in his or her hardware. So quantum hardware vendors are looking for universal set of operators, in the sense that any qubit operator is a finite combination of operators from this universal set of operators, as usual, right? And if you use a one qubit operator, then it's a very simple exercise. Each manipulation in C2 in the complex vector of 2 dimensions can be rewritten as a rotation around the z-axis, around the y-axis, around the z-axis again, right? This is an indication any qubit manipulation consists out of 3 rotations. One around the z-axis, then around the y-axis, then around the z-axis in different angles. Very easy algorithm. If you see the proof, it's a constructed proof. You need to solve a linear equation system, and then you find out what the angles basically are. It's an exercise that you have in my lectures. If Kazun once would come for 3 months and give the lecture here. Okay. So every one qubit operator is a composition of rotations on the Bloch sphere. And that means the set of Pauli operators, X, Y, Z, are universal for one qubit operators. So hardware vendor only needs to implement X, Y, Z in its machine, and then it can manipulate each and any qubit according to this formula. And by the way, all compilers are using this formula in order to compile a unitary matrix down to X, Y, Z. We discussed what quantum registers are, and now we are looking for a universal set of multi-qubit operations. We found a universal set of single qubit operations. We want to find a universal set of multi-qubit operations. And here I need to introduce the controlled NOT operator. The controlled NOT operator takes 2 qubits, X and Y, leaves X intact, and takes the modulo 2 addition between X and Y as a result of the Y statement. So if X is 1, then the state of y will be negative, because if y is 0 and x is 1, the result is 1. If y is 1 and x is 1, the sum is 2, modulo 2 is 0, and so on. So this is the controlled NOT. This is the control bit, this is the target bit. Right? This C0 is a unitary operation, and its graphical representation is like this. The controlled bit is here with a dark dot, and this is the symbol of the plus sign. This is the plus sign on the qubit that is the target bit. Right? And the connection says that this is the control bit, this is the target bit. And C0 is the important workhorse to create entanglement. Right? So if I have, so you remember that this state is a separable state here. Right? We had that before. And if I apply this, and it can be achieved by Hadamard, we will see that. If I apply C0 on this state, so C0 is a linear map, I can apply C0 on the component vectors on this and this. If I apply C0 to 0, 0, I get 0 out, because the control bit 0 is 0, so no negation is done here. But here the control bit is now 1, that means I negate the 1 state into 1, 1. And this is the Einstein-Podolsky-Rosen state. That means out of a separable state, C0 can generate an entangled state. It's thus easy in a quantum computer to create nano black holes and wormholes in space, right, in order to entangle qubits. And if I take this entangled state here and I apply C0 again, if I apply control NOT to 0, 0, right, the control bit is 0, the target will be left intact. This is this one. Here the control bit is 1. That means I need to negate this one. This remained intact. This turns to 0. And this is the original state above. That means C0 controls creates entanglement and can get rid of entanglement. Please.
Yes, you mentioned about that qubits entanglement creating wormholes and black holes.
Yeah, that's the current theory. Yeah, that's the current theory. Don't take it too serious.
There can be white holes also on the other side. White holes on the other side.
No, the theory is from qubit doesn't speak about white holes.
Okay.
No, not at all.
Okay.
Yeah.
Thank you very much.
Welcome. If you're interested, I can send you tons of links to prepare. It's a very interesting theory. Unbelievable. So C0 can transfer into separable states. So entanglement. This is a topology we saw before, a topology of a chip. And these two qubits can be entangled immediately because there's a connection on the chip between them. Right? These two qubits can't be entangled. I can't apply the C0 here because there's no connection between the two qubits. That means the connectivity of a quantum chip is absolutely important. If you write down your circuit, right, then you need to run a compiler. In this case, it's called a transpiler. This name has been established in quantum computing. They have a transpiler that understands the chip, where you need to transpile your circuit to, right? And the chip understands the topology and massages your quantum circuit, because what I need to do is I need to move this qubit. I need to move this qubit to this qubit. It's called a swap operation. So if you write down your quantum circuit and you transpile it, additional operations are injected that are injected because of the very well-known topology of the qubit. It makes the quantum circuit more broad. It increases the depth of the quantum circuit. And the more depth the quantum circuit is, the more unlikely it is to be executable on today's machines. Because today's machines are noisy, we will discuss that, are noisy. That means you must take care that your algorithm runs as short as possible, as quick as possible in a quantum computer. So the physics has a deep impact on which algorithms could be run today on given machines. Here you see other chips by other vendors, not only IBM. This is Rigetti, another superconducting vendor. So, and that basically means we wanted to find a universal set of unitary operations between n qubits, and the theory is that the set of 1 qubit not the theory, the theorem is the set of 1 qubit operators n C naught is universal. So each and every unitary matrix in between n qubits can be rewritten by manipulating individual qubits and C naughts between 2 qubits. Right? Pauli matrices and the universal 1 qubit is universal here. That means for an n qubit operator, the number of required n qubit operators, n C naught, is, oh gee, there's a problem. The order of magnitude is n squared times 4 to the power of n. Right? In order to rewrite a unitary, I need exponentially many number of 1 qubit operators in qubit. This sounds to be a performance problem, right? Because if you have 400 qubits, 4 to the power of 400 is huge, right? So this indicates something that is a problem, right? So this is not an efficient implementation of quantum register operation. But remember, algorithms are random experiments. That means if I repeat the execution of a unitary operation with subsequent measurement produce a probability distribution. We mentioned it before. The result with the highest probability is the result of the execution. This is what we discussed before. Okay, sorry. And now another theorem, Solovay-Kitaev theorem, says that HST, we introduced this 1 qubit operation, and C naught is a set of operations that you can implement, and you can approximate each and every unitary by a composition of these operators. What does approximation mean? It means the real distribution that got produced by the unitary operator that you want to run in your computer can be approximated as follows. You can take a tube of width epsilon around the blue distribution, which is the blue distribution, and you can find an approximation of HST C naught operation that stays within this epsilon tube. That basically means that the statistics of measurements don't really differ. The smaller I make the tube, the closer is the orange distribution to the blue distribution. And that means, but because everything is a random experiment, I only need to find a distribution that is close to the real distribution, the real result. And for this, you need log square 1 divided by epsilon, right? And this is something that is done in each and every machine, right? They rewrite a quantum circuit based on these kind of operators here, right? And you define what the epsilon is, right? How precise your approximated distribution must be to a real distribution, and then the algorithm, the transpiler does it. This implementation is separate, this is done. And this basically means you have a quantum algorithm. You have here 2 qubit operator with this C naught. You have 1 qubit operator. And all operators that can be run in parallel because they don't interfere is called a layer. In your algorithm, you apply algebraic operations to shuffle around to shift around the operators so that they fit into a single into a single layer, and then the number of layers that remains is called the depth of an algorithm. All these operations are executed in a single step, right? Layers are performed in one step of the quantum computer, right? But the more layers you have, the longer the execution takes. Here's an example. This algorithm can be rewritten as follows, right? I can shift this 2 qubit operator down here. I can shift this here, and what remains is a 2-layer operator, right? This has a depth 2, and breadth. Breadth is the number of qubits that need to be manipulated. Here is another one, a real one. What you can do is you can shift this S beneath H. You can shift this H also over there, and what then remains is this circuit. It has a depth 3 and the breadth 3 because there are only 1, 2, 3 qubits manipulated. The other 2 qubits are not manipulated at all. But there is noise in quantum computers. Noise, as I said before, this is the Hadamard thing, the matrix that generates superposition. The Hadamard matrix can be rewritten. It's a 1-qubit matrix. It can be rewritten as rotations around the z, y, and z axis by different angles. You can easily compute that this is the Hadamard matrix, right? And you rotate, that means manipulation of a single qubit are rotations around angles. Although you can rotate exactly around 180 degrees and 45 degrees, you can't rotate exactly around 3.50003 point blah, 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 an irrational number there, right? That means each rotation has a little error, right? Because you can't exactly rotate around each and every angle, right? The rotation cannot be formed precisely. That means quantum operators are inherently noisy, erroneous. And qubits are also interacting with their environment. They are unstable. So what one of the vendors we work with is they had deep in the cellar a quantum computer, and they observed strange phenomena that the qubits were shaken. And they didn't know what happens. We know that qubits are unstable, but it happened that there is a pond close by. And there was a population of goose. And the goose were swimming slowly on the pond, and with the gooses at the sudden wanted to fly, right? This shaked the ground, the little shakes, and destroyed the state of the qubits in the quantum machine, right? So they are so sensitive. Or it's known that particles from outer space come and hit the qubit and destroy the state. This is why they are down in a cellar, a lot of concrete around it to protect them, right? So qubits are a matter of decoherence. They decay over time. That means a quantum algorithm cannot be performed for an arbitrarily long time. It cannot obtain not contain arbitrary steps. That means algorithms are typically noisy, right? Qubits may decay. The operations have some errors. So a certain very simple rule of thumb applies, that the width of an algorithm, the number of qubits manipulated, times the depth, the number of layers, is less than 1 divided by the error rate of the quantum computer. And the error rate is something that combines the decoherence time of the qubits and the imprecision of the rotations. This has implications, but we will discuss error corrections in the afternoon still. The consequence is you need to decide whether you want to run a deep quantum algorithm. Deep means D is large, but then W, the width, must be small. So if you want an algorithm that has many operations, you only have time to grab a couple of qubits and manipulate them. A shallow quantum algorithm can manipulate many, many qubits, so W can be very high, but then D, the depth must be small because W times D must be less than the error rate, right? Johanna and other colleagues, we have a paper here on this one. By the way, I'm absolutely happy to share the slides with you. Yeah, Kasun, you need to tell me to whom to send, and send a mail to Kasun. Yeah, and then he will distribute the PowerPoint, or you have a website where you put that. Okay. Or I can store it somewhere and send you the link. So shallow quantum, and the shallow quantum algorithms, because they use many qubits, they have potential for quantum advantage as of to now.
These rays like particles like neutrinos also interfere with the qubits.
What, chaos?
Neutrinos.
Nucleon.
Neutrinos.
Neutrinos.
Yes.
No.
Can
They are too small. They don't. As far as I know, they don't interfere with the qubits.
Okay.
Yeah. As far as I know.
Okay.
Yeah. So this is why these days, to show advantage of quantum computers, You use shallow algorithms, algorithms that have only a certain amount of operations that are performed, but many qubits, because you can't simulate computations with many qubits. Come on. And these machines that are a matter of decoherence and imprecision in operation are called NISQ machines. Noisy, because there's noise. Intermediate scale, although because we have less than 1,000 qubits available these days, quantum computing. And we will discuss that a bit later. What I'm now going to do is explain to you a little bit of tooling, right? It's impossible that you invent your own Hamilton operator, unitary matrices, your own circuit, but there's tooling, very nice graphical tooling around. So, here's the architecture of the tools that are around. There are different tools around from different vendors, but this is the, yeah? You need the microphone.
You mentioned that the Hamiltonian has to be manipulated when designing the algorithm, or that's how I remember it. Now, the Hamiltonian operator gives the total energy of a system.
Yeah.
So what's the significance of Hamiltonian for the state? Is it because the time-dependent Schrödinger equation relates the wave function to the Hamiltonian operator with its variation in time? So we use that equation to find new states, and those new states are not like, we don't need to know the energy of the system at that state, because we can define a quantum state in the, like, for quantum computing applications, like the spin, where the spin of the state is the like manipulated quantity in the quantum computer. So those new states that we calculate using the DSC, do we like operate the spin wave function on that to calculate the new spin of the state?
No. So, no, because this would be hardware dependent. So we are collaborating with quantum physicists. How they invent the Hamiltonian, what their understanding, their gut feeling behind this, how energy depends on the evolution, I have no clue at all. Right? I completely rely on the quantum physicist. He comes up, Frank, this is, you described the problem to me. This is the Hamiltonian that describes how optimization works, how this works. Now compute the unitary. I have no clue at all what happens there. I don't want to understand that. So the answer is very honest. I have no clue.
Okay, thank you.
Yeah. Okay. Disappointing, but honest. Yeah.
Thank you.
Okay. Sorry. So this is the architecture of the overall tooling, right? You have here your quantum processor, QPU. You have the classical processor, CPU, because if you want to test your quantum circuit, you test it with a small amount of qubits on your quantum, on your classical machine, sometimes even on your laptop that you have, right? And this is why you have a simulator of your quantum algorithm on a CPU. The quantum assembler is an assembly language, a very low-level language that describes how your circuits look like, and then they have higher-level programming languages like Qiskit, for example, that are compiled down to the assembler. And then you have a bunch of tools like the compiler that I mentioned before, some libraries for particular application areas, and so on. Testing. Testing is very interesting. When Johanna and I visited the very first time the quantum physicists we are collaborating with, or the first quantum physicist we collaborated with, we were exchanging information. What are we doing? He said, oh, I invent quantum algorithms and I work with it. And being a software engineer, I asked, how do you test it? He said, what do you mean? I said, yeah, you want to test the algorithms that you have written. He said, what does testing mean? Yeah, try to find errors. He said, now I understood. I'm a physicist. I never do errors. right? So this is how two different worlds come together. Right? We always think as computer scientists there's a lot of testing that you need to do in order to fix your code. And physicists said, why? But he now in the meantime learned, and there's a research area coming up, it's evolving, testing in quantum computing. How do you test it? Because you can't set breakpoints, you can't inspect what your algorithm currently does because it would destruct the information, right? So it's a completely new kind of testing that people need to invent to test quantum circuits. But the simulator here allows you to run with a small amount of data load on a CPU to find out how your algorithm does behave, is some sort of initial testing that we have. And here you see a tool by IBM. It's a graphical tool. Here you have the qubits, and you can add more qubits very easily. Here are not only the Pauli matrices, the rotation, the CNOT, and so on, but a bunch of others that you need too, right? Here you see the immediate result. Here the system is in ground state. I didn't do anything, so the system is in ground state 0, 0, 0. And here you see the quantum assembler language, right? It's a programming language, very low level. And when we step through example, you see it evolving. Now what I do is I take the Pauli X to negate the 0 to a 1, and then you see the state is 1, 0, 0, 0 down here. And here you see the quantum assembler set. I use the Pauli X matrix on the qubit Q0, which is the upper 0 here, and then I perform a measurement and store the result of the measurement in the classical bit C4. Why does it say C0 here? No clue at all. So, okay. And then you have the simulator. I run my algorithm, then the simulator runs and says here what the outcome basically is, right? If I run the same on the QPU, I invert the first qubit from 0 to 1. If I then run the same algorithm on the QPU, so the simulator said in 100% of all times you reach this state. But if you use a real quantum computer, you found out there's a certain chance that the final result is 0, 0, 0. Right? Most of the time, I measure 1, 0, 0, 0, but there are some chances for 0, 0. So the probability, this is one of the causes that the most probable result is the result of your algorithm. That's the first indicator. You take the distribution, and the most likely result is the result of your computation. Next, our next experiment takes the Hadamard operator on the first qubit, and we already know that the Hadamard operator on the state 0 creates superposition, right? Here again, I take the Hadamard operator H on qubit 0, and then I measure it and store it in a classical bit. And on the QPU, you see that this is true. I expect 50% 0, 50% 1, and roughly this is 50% 0, 50%, and the rest is noise, right? There's some error, some noise going on in your quantum computer. But the distribution is an equal distribution, so this is fine. Then if we take this algorithm here, it has the depth 2, right? It has the Hadamard on the first qubit, and after putting something into superposition, I apply the CNOT. So I create here, what happens here is I create the EPR state, the Einstein-Podolsky-Rosen state. And if I run this simple circuit on a real hardware, the compiler runs and generates this complicated beast out of it. At the sudden, I have the depth 7. That means my quantum physicist said, this is the algorithm to run, very small and tiny, and you stupid computer scientist, you can run it. And then I go back and say, no, I can't run it. Take a look at this one. It has depth 7. It can't be executed. In fact, it can be executed. But you see that transpilation, in most cases, increases the depth, right? And the more depth I have on today's machine, I cannot manipulate as many qubits as in a pure algorithm, right? So when you have an algorithm, you always need to run the transpiler and check the transpilation result and find out whether it could run on a machine. And the system that I very briefly mentioned at the end of my part of the talk is we also have tools called the NISQ analyzer that analyzes quantum algorithm and tells you this algorithm can be run on this piece of hardware. So we have tooling that helps you as a computer scientist to find out which machine to use in order to let the algorithm successfully run. And what happens here, what I said before, Hadamard followed by a C0 generates in this kind of state here. Right? I created entanglement. This is the EPR state. And this is again, if I measure, I have 50% 0, 0, 0 and 50% 1, 1 on QPU. So tooling. There, several companies have several tools. There is tool. It takes it takes some learning curve to work with the tools and with the languages, right? It's not very simple, but not too complicated. But now we dive into the first algorithm that showed exponential speed up a couple of decades ago. It's the so-called Deutsch-Joscha algorithm. The problem is you have a coin and you want to find out, is it a real coin or is it a bogus coin that only has two of the same sides? So you have a coin and you want to find out it's bogus or not. And the question is, can you find out by flicking the coin exactly once? Classically not. Right? You have a coin, flip it once. You don't know, you see head or tail, but you don't know what the other side is. So classically, you need to throw at least twice. Right? You can do this, but in quantum computing, you can do it. So how do we do it? We abstract the coin flipping by a Boolean function. Here I take already n coins, a Boolean function. We call such a Boolean function constant if f of x is always f of y. And we call it balanced if the number of zeros is identical to the number of ones that the map produces. So it can only produce two values, yeah? And so the f maps half of the domain to 0 and the other half to 1. And the problem is we need to determine with the minimum number of evaluation of the function, whether the function is constant or balanced, whether all coins are bogus or whether all coins are correct coins. The classical case is, right, you have to read half of the values, and even if you have read half of the values of such a function, you are not sure whether the function is constant or balanced. Because if the first 50% are 0, right, you don't know is it balanced or constant, because if you read one value more, and this is a 1, you know it's balanced. If this is also a 0, you know it is constant, because it is either constant or true. That means, classically, you need to have 2 to the power of n minus 1 plus 1 evaluation in order to find out whether the function is constant or balanced. Now we define something that quantum computing guys call an oracle. An oracle is, for computer scientists, a subroutine. Right? It's a subroutine that you run in your quantum computer. We have an oracle that maps 2 qubits as follows. You have x, y. X is remain intact, and y is added modulo 2 with the value of f of x. Right? This is an oracle. This is, you can prove that, a unitary transformation. And this is now the overall algorithm of Deutsch and Joscha. You don't need to understand it completely. I only want to show you how the algorithm looks like in paper. You have the coins here, x, and you have the indicator whether something is bogus or not. This is y. So you initialize the quantum computer in this way. Then you apply the Hadamard transformation on the register. You store it again in the quantum computer. Then you run the oracle on the quantum computer, right? And then you apply the Hadamard transformation again. And if you now measure, and you measure 0, that means the most frequent result is 0, 0, 0, then your function is constant. If you measure a value different from 0, 0, 0, you have a balanced function. So this is the distribution that comes out, right? If you measure 0, 0, 0, and in this case, the most frequently appearing value is not 0, 0, 0. That means the result is not 0, 0. The function that I have evaluated here is balanced, right? Because the value 0, 0, 0 is not the most frequently occurring one. This is why the shape of the distribution is so important. And here, what you see is, I throw the coins only once. UF is the, I flip the coin, right? I flip it only once, and then I know immediately the result. That means the algorithm evaluates f exactly once. In the classical world, I need to evaluate it 2 to the power of n minus 1 plus 1 times, which basically means I have an exponential speedup. This is the worst meaningless algorithm on this planet, right? There's no practical applications, right? Why should I find out by throwing a coin once? But it shocked the computer science community as well as the physics community that here the first time in history we had an algorithm that showed an exponential speedup of a problem that needs exponential many steps in a classical case. And this kicked off enormous research in area of quantum computing to invent quantum algorithms that show some benefit compared to classical algorithms. And by the way, this is another aspect of quantum computing because if I apply the oracle, what you see here is a value table. The result of applying the oracle is you have here the elements in the domain, and here you have the values of the elements in the domain. It's a value table. In a single step, you compute the complete value table of a function. Right? That is, if somebody wants to have the cosine of all values between 1 and 1000, right? You have a single step, and then the quantum computer, you have the value table of x cosine x for all x between 1 and 1000. This is quantum parallelism. A single step produces a huge value table, which already, yeah?
Does it include the irrational numbers also?
If you encode them, in practice you only have rational numbers, right? Yeah? We will come to encode how to encode data in 30 minutes. Yeah? But here, of course, you need to say which x should be used in order to include f of x, right? So in a single step, you produce the complete value table. This gives already an indicator what kind of problems are extremely suitable for quantum computing, namely to determine global properties of functions. Remember the Deutsch-Röscher problem. I have n coins, I want to throw them, and then I want to find out whether all are bogus or whether there is whether they're all correct. I computed in a single step the function that contained for each coin whether it is a real coin or a bogus coin. We will see in a couple of minutes that I use this trick, this oracle trick, to determine periods of functions. And if I can determine the period of a function, I can crack keys. Again, the period of a function is a global property. The sine function or cosine function is a global property, is the periodicity. This will be another example of the applicability of quantum computing to determine global properties of functions. So all problems that can be reduced to determine global properties of function is a fantastic source for quantum computing, a fantastic application area. This is quantum parallelism. I leave out search, right? This, unfortunately, and I want to briefly mention what about complexity of algorithms. So we call a problem of the class BQP, meaning bounded error quantum probability. If it can be solved on a quantum computer with error probability less than 1/2 minus epsilon. Epsilon is some sort of constant that is algorithm specific, right? And BQP, this class of algorithm, is what P, polynomial algorithm, is in classical computing. You want to have a BQP algorithm because this runs fast on a quantum computer and produces very, very fast exact results, right? So if you are used to these kind of diagrams in theoretical computer science, you have P, you have NP, you have the polynomial time hierarchy, and BQP contains P, but goes beyond it. In fact, in BQP, there are problems that can only be solved with a quantum computer, not classical at all. This is also absolutely new, right? There are problems that can, in principle, not be solved on a quantum computer. but they can be solved on a classical, but they can be solved on a quantum computer. By the way, this was a long-seeked result. Nobody could find it, and it was at the end of the 18-something in a bachelor thesis by an Indian student in the US. Right? It was a bachelor thesis who found a problem that can only be solved on a quantum computer. Very interesting. And this big Q piece is important because of something we call the Chernoff bound. Well, the Chernoff bound is the probability to output the correct result. So the probability to output the correct result increases exponentially with the number of repetitions of a quantum algorithm. So that means that the probability that you spit out a wrong result is less than e to the power of 2n epsilon square, where n is the number of repetition and epsilon is the error that I will need to tolerate. Very easy 10-minute proof. And if omega is the maximal probability that you accept the wrong result, you can, it's a 7-minute proof, you can prove this formula. The number of repetition that you must perform in order to be sure that within the probability omega you only spit a correct result is 1 divided by 2 epsilon square. Epsilon is this constant that you produce errors with probability less than 1/2 minus epsilon, and this is the error you are will need to tolerate. With this number of repetition, you get the correct result with this probability 1 minus omega. That means, as an example, if you have an algorithm with epsilon equals 1 divided by 4, and you are willingly with 1 divided by 1,000 to accept the wrong result, you need to run your algorithm 56 times, and then you are sure with 99.99% that the result is correct. This theorem, this little lemma, is the origin why we run a quantum algorithm not once, but a couple of times. Not only because we want to get the error, the probability distribution, but this Chernoff theorem proves you that if you run the algorithm more often, you are absolutely sure when you get the final result. And now I mentioned global properties of functions. And global properties of functions are important. Here's another example. This is the algorithm RSA. RSA is the workhorse on our planet to have secure communication, to have secure encryption, and so on. It basically works as follows. I rush over it. You pick 2 large prime numbers, p and q. You multiply them to get a natural number, and then you compute the so-called Euler function. The Euler function reduces p and q by 1, multiplies it, and then you get phi of n. Then you choose a small g. G is your secret key, such that phi of n and g are co-prime. It sounds complicated. It means that the greatest common divisor between phi of n and g is equals 1. And then you determine a solution d of the equation d times g congruent 1 modulo phi of n. It sounds also complicated, but you use the Euclidean algorithm. It's a polylogarithmic algorithm. It runs pretty fast. And this happens every day when you open your browser, or if you do online banking, or you buy at Amazon or something. It happens every day. The number d that you compute here and the number n that you computed here is your public key, and this number g is your private key. Then you destroy hopefully everything except, and you keep the private key secret. And here's how a message is encrypted. You take the message and map it into a string of bits, right? And then you compute for the string mu to the power of d. D is part of the public key. Modulo n, n is part of the public key. This is then the encrypted message, and you need to decrypt it by taking the encrypted message, take it to the power of your secret key, modulo n, and then you get the message back again. This is RSA. And this happens millions of times per second as we speak. How do I crack your key? Cracking your secret key, G, means to determine phi of n. Because if I have phi of n, I can solve this equation because D is part of the public key, then I can compute G in logarithmic time. Pretty fast, right? And phi of n, how can I compute phi of n? Well, I need to know n part of the public key, what the prime factorization is, right? if I can factorize the number, I can determine phi of n. If I can determine phi of n, I can easily compute your secret key. But there are only exponential algorithms known to do prime factorization, luckily, right? There is no proof that there won't be any classical algorithm to factorize numbers, but because for many decades we didn't find a classical algorithm, we all believe we're absolutely safe, which is a mistake, right? Because I need to introduce a function called the exponential module function, module exponential function. So I take an arbitrary number a between 0 and n. N is the product of the prime numbers that you basically took. And then you define an exponential function at the basis a. You take a natural number, x, compute a to the power of x modulo n. This is the exponential function. Now let's take a look to this value table. I have chosen a equals 2 for simplicity. 2 to the power of 0 is 1. If I divide it by 5, it's 0, and the remainder is 1. Sorry, the remainder is 1. Then I take x equals 1. 2 to the power of 1 is 2. Divided by 5 is 0. Remainder 2. This is here. If I take x equals 2, 2 to the power of 2 is 4. Divided by 5 is 0. Remainder 4. If I take x equals 3, 2 to the power of 3 is 8. Divided by 5 is 1. Remainder is 3. 2 to the power of 4 is 16, divided by 5 is 3, remainder is 1. And now at the sudden I see it seems to be that the values are repeating. It seems to be that this function is periodic. And in fact, we call the function, so it's f of 4 plus x is f of x. F has the period 4. And it turns out that this module exponential function is periodic. Right? You can compute the period. And we say that this function has period p if x of p equals f of x of 0, where p is minimal. And if this is true, x of p is a to the power of x mod n, a to the power of p, x is equals p of n, and x of 0 is a to the power of 0 modulo n, right? And a to the power of 0 is 1 modulo n. Right, and this is defined that a to the power of p is congruent 1 modulo n, and it means that n divides a to the power of p minus 1. That means there's a natural number k such that k times n is a to the power of p minus 1. That means if x has the period p, if and only if a to the power of p is 1 modulo n. You believe me, right? So this is simple. Cracking keys. Assume we can determine the period of this exponential function. Then we know that a to the power of p, last slide, is 1 modulo n. That means there's a k such that k times n is a to the power of p minus 1. Now we assume that the period is even. If the period is not even, I choose another a. I can choose a between 0 and n is a huge number in RSA, right, in the order of billions, right? And there's a theorem in number theory that even periods occur much more often than uneven periods. Very interesting. So I assume that p is even, because if p is even, I can divide p by 2. This is a natural number, and I can use the binomial formula that a to the power of p minus 1 is a to the power of p half minus 1 times a to the power of p half plus 1. And this product is k times the number n that you know from RSA. That means that if this equation holds, k times n is equals this one, either n and this has a common divisor, or n and this has a common divisor, right? It's a product here, right? That means that the greatest common divisor, or the greatest common divisor of them, is a divisor of n, right? That means if we can determine the period p such that a to the power of p equals 1 modulo n, we can determine the divisor of n. Iteratively, you can compute the prime factors of the number n. We can crack keys. So factorization means to determine the periods of the exponential function. Yeah, this is a new insight. Factorization means period of the number theoretic exponential function to be computed. And now back, you have heard about Fourier transformation. Fourier transformation is something that can determine periods of functions. Right? Theorem of Fourier said any function can be written as an infinite series of periodic functions. So we use now Fourier transformation. Now a big step. This is the matrix that performs Fourier transformation. These are the roots of unity of complex numbers, right? This is the matrix here. And this matrix, I won't discuss it, performs Fourier transformation. This is a unitary matrix. You can transform this unitary matrix into a quantum circuit, rewrite it as 1-qubit manipulations and 2-qubit manipulations, C-naughts. And this basically is Fourier transformation is matrix manipulation. Here's the circuit. I'm not discussing what the circuit does. This is a quantum circuit that implements function Fourier transformation. And Fourier transformation can determine global properties, namely periods. This is the Shor algorithm. By the way, Johanna and I wrote a paper. What happens in this classical part here, right? I will briefly discuss that. So, Shor says I initialize my computer, my quantum computer, in the ground state. I split the state in two halves. Then I apply the Hadamard transformation to the first part, to the A part, leave the B part intact. I get this state here. And now I apply an oracle, and the oracle function is this Fourier transformation, the quantum Fourier transformation. And then I get the value table of this exponential function. So the oracle function computes the module exponential function. In a single step, I have the value table of x and a to the power of x modulo n. And then I need to inspect it, right, based on quantum Fourier transformation, and then I get the value a out of it. This is not yet the period, right, but you need to apply number theory. You need to do something that's called continued fraction evaluation, right? Each number can be written as continued fraction, and if you rewrite as continued fraction, one part fraction is then the period p, right? And this is the quantum part. We use superposition, we use entanglement and parallelism, and then we determine the period by measuring that, and so on. And then we need to post-process. The computation of continued fractions is post-processing that I need. So the only use of the quantum computer in this situation is to run the quantum Fourier transformation to get in the quantum computer the value table of the function that I know is periodic. So this is the algorithm, the Shor's algorithm. The only thing I use the quantum computer. So overall, so the runtime of the algorithm is polylogarithmic, right? Here is the part where the quantum computer comes in, and here you see the best known classical algorithm show this exponential behavior, and Shor's algorithm shows a logarithmic behavior. That basically means if you have an ideal error-corrected quantum computer, but as I mentioned an hour ago, today's quantum computers are noisy, right? We are not yet here. It shows that the RSA 2048 challenge, so the RSA, we use 2048 size numbers that are our keys, and this number has been chosen by will because the fastest algorithm known runs for the lifetime of the universe to crack a key. And we thought for the last decades, this is good enough, right? This is good enough. Who lives forever, right? So, and in 2018, you needed this 13 billion years to crack a quantum computer, an ideal quantum computer that runs with 1 megahertz or 1 gigahertz, runs in a couple of seconds to crack keys, right? And the number of qubits that you need is, so we need a cryptographically relevant quantum computer to crack keys. That means if n 2048 is the size of your key, you need 5n plus 1 qubits and 4n to the power of 3 operations, gates. And that basically means for RSA 2048, we need 2048 NS 2048. We need 10,000 qubits if you use this sphere, and you need a couple of billion operations. Today, we only have 400 qubits available, and we can run 1,000 operations. This seems to be impossible for the next years to come, right? And if you go to a CEO of a company and say, oh, you are in you are in trouble, right? You are in trouble, then the CEO said, my guys told me this is long ago, I don't spend any money. But then you can argue the other equations, Moscow equation, you can argue with the CEO how long it takes to change all the infrastructure in the company so that it becomes quantum secure, right? And you ask the CEO, how long do you need your data confident? And most people say 20 years, 50 years, right? And then you say, well, IBM, Rigetti, they plan to have a cryptographically relevant quantum computer available end of this decade or early next decade. You need to store your documents for 50 years confident, but you need 3 or 4 years to change your infrastructure. You're already now in trouble. The US, for example, has a law released a couple of months ago that a CEO who brings his company in trouble because it doesn't react to the quantum threat must pay out of its own pockets any damage to the company. In the EU, they are preparing the very same. And since a couple of weeks, CEOs are extremely nervous because paying out of their own pocket, they don't like it. The US government is changing everything to make their systems quantum secure. They are already reacting, right? The Google Chrome browser that you have is post-quantum secure. There's a flag that you can switch on, and then you are quantum secure as long as you communicate with Google backends. Internal communication in Google is absolutely quantum secure. And so I can continue and continue. So big companies are reacting, smaller companies are not even aware of the problem that is currently happening. Yes?
Could you give me examples of quantum problems?
Cracking keys. Computing so what are quantum problems? Any problem where we only know exponential algorithms for can be turned based on quantum algorithms into BQP, algorithms that can in polynomial time solve problems on a quantum computer. And I'm discussing here this cracking key problem, but you have optimization. So for example, I think it's there are airports that are already, there's a problem in the airports called the gate assignment problem. If an airplane comes in and they would like to give you a finger where the airplane can basically touch, it's an NP-complete problem, very hard problem, right? This is why we all, when we land, we need to get into the bus, and so we hate it. So solving this problem can be done on a quantum computer based on annealing. Right? In production, some airports already run on the quantum annealer the gate assignment problem to make our life more easier. There are people who build trucks, and what they have built in is solving the traveling salesman problem, even a worse problem, the dynamic traveling salesman problem. The scenario is you have packets, you scan the address of the packet and you pump it into the truck, and then you want to compute the fastest route so that the person who's delivering the packets is early at home in the evening. So you need to solve the traveling, but in the city there may be traffic jams. So the route that you compute by loading the packets into the car may be invalid after a couple of minutes or after 1 hour. You need to recompute it, but it takes a long time, classically recompute, and so on. There's a lot of different use cases for quantum computers based on problems that you can't solve classically, right? And there are books which kind of problems can be solved. There are samples. I will show a link to a platform where we describe a bunch of problems we solved, not we, our consortium solved with industry partners based on a quantum computer. You are not yet a believer. So it seems to me that we are safe for some time. But there is an advancement. So what IBM and another consortium showed, that you can use 24 qubits to realize a qubit that is errorless, faultless, because this is a logical qubit, right? That means we saw that we need 10,000 logical qubits to run the Shor algorithm correctly, right? That means we need 240,000 physical qubits, and this is expected in a very few years, end of this decade or early next decade. That's what I mentioned. But even now, there is a group that factorized this number with only 10 qubits based on this Quawa algorithm, right? So they use this algorithm today and crack this thing, and they expect that their algorithm can be used with 372 qubits. We have 400 qubits available to run with to crack RSA 48, right? So this is on today's NIST machines. So we are getting close, but they need a depth that is too high for today's machines. So the number of qubits are there, but the number of gates that you need to run is too high. But we are getting close here, right? And Johanna and I also have a paper on arXiv on post-quantum security, what the world is doing to protect against this threat. Again, there's a lot of work going on in NIST standardization work. NIST means National Institute of Standards in the US. They are standardizing post-quantum secure algorithms that are based on lattice-based algorithms, completely different. The world today depends on prime factorization, RSA, or elliptic curves, ECC, elliptic curve cryptography, but also elliptic curve cryptography can be solved by Shor's algorithm, because Shor's algorithm is in fact not computing periods, but discrete logarithms. And discrete logarithms can be used to crack elliptic curve cryptography. So both schemes that we use today, ECC and RSA, can be cracked on quantum machines. We need to be innovative, standard something completely different, which is based then on lattice-based cryptography. And this lattice-based cryptography is crazy, right? A lattice is a discrete set of points in the vector space, and the vector space of the standards are vector spaces that consist out of tuples of polynomials, right? So you have vector spaces that don't consist out of points, but each component is a polynomial of a high degree. You need to multiply polynomials, you need to divide polynomials, you need to add them, right? And these algorithms are quantum safe in the sense nobody as of today knows how to crack these mechanisms, classically or quantum, but there is no mathematical proof that they cannot be cracked, right? That means we are yet on another bet that our infrastructure is safe. But NIST is constantly standardizing these kinds of algorithms, so if one algorithm is cracked, you can plug in the to-be-built infrastructure a new algorithm, right? This is called adaptive cryptography, right? You need to have an adaptive cryptographic infrastructure where you can plug in new algorithm on a constant pace, right? A lot of effort, a lot of effort. The physics solution would be to communicate based on qubits, to not send classical information, but quantum information, because quantum information cannot be copied. You cannot, as a bad person, take the information, take a look at it, because it destroys, and stick it back again. So there are not undetected attacks on quantum-based security mechanism. But this quantum-based security mechanism require a completely new hardware infrastructure, right? You need laser beams, the qubits are then sent as photons on the laser beam, and the laser beams must be established from between the communication partners. For example, China is connecting two cities based on laser. They have a geostationary satellite. They encrypt information. They transform information into quantum information in qubits, send it to the satellite, reflect it to the other city, and you can't break this because any adversary will be detected because data cannot be encrypted. In Europe, each European country is building this laser infrastructure, And most countries already have built that between selective city. And again, think from 26 on, they will connect the different countries. So this is experimental work that works between cities. Of course, the governments and military organizations communicate this way. This is the secure communication, but incredibly expensive. Incredibly expensive. Right? Second? It's a it's very hard to hear, sorry, sir. Here's the microphone.
Can't we use the fiber communication for that instead of satellite?
What kind of information?
Fiber. For optic fiber. Optic fiber.
Yeah, you can use optical fiber, but they have physical problems because the qubits decay after a couple of 100 meters. How much was it? So you need to have amplifiers to do that, but amplification, no cloning theorem, is difficult. You can't capture them. Yeah? This is why they take laser lines, right? Smart question, and you are concerned. This is good. Yeah. So error correction. So machines, as I explained them by now, are error prone. The qubits decay. The individual gates show errors here. And you may say, as a computer scientist, we have tons of error correction algorithms, but you can't use them because the classical error correction algorithms depend on being able to copy information, for example. But you can't do that because of the no cloning theorem, right? Or a qubit does not change in a discrete manner from 0 to 1. But you have continuous errors. A qubit on a Bloch sphere may only dangle around a little bit, right? There are not discrete errors, but continuous errors. But all classical error correction algorithms depend on discrete errors. And so on, and so on, and so on. So error correction doesn't work. But there is a new quantum error correction mechanism, or a bunch of error mechanisms. For example, I can encode a single qubit in 9 qubits. So for example, if I represent 0 as this monster state, it's an easy circuit that I can basically build here. 1 as this state, there are many other encodings that are discussed. Then I can correct single qubit errors. Right? I represent 1 qubit as 9 qubits, and if 1 qubit fails, so it's an error, I can detect it based on this encoding. I will briefly discuss with you how it basically works. But of course, if you have 9 qubits, in order to protect, to represent 1 qubit, if 2 qubits fails, this algorithm doesn't work anymore. And it may be that multiple qubits basically fail. But the message here is, you need to use multiple noisy, we call them physical qubits, to realize one stable, we call them logical qubits. So you need much more qubits. Here's how it works in principle. You have here one quantum state, psi, and you want to encode it in this kind of error code. Believe me, this basically computes the crazy 9-qubit thing that I've shown before. Then I have replicated the information, not copied, replicate the information. Then I do some computation. During the computation, some noise may happen. And then I have a circuit that's called the syndrome recognition circuit. It can detect, it's an exercise, okay. You can detect an error. You can detect which qubit has been manipulated. And this circuit basically repairs the error immediately. Yeah? You don't copy it, right? This C0 entangles the information. Remember, C0 is doing entanglement, right? This circuit here, oh, where am I? This circuit here takes the state here, entangles it with a 0, entangles it with a 0. It doesn't copy it. This is this absolute fancy trick. It entangles it, right? No copy because no cloning is disallowed. That means, next slide, I need, in order to create one logical qubit, error-free qubit, I need a block of physical qubits. So I multiply the number of qubits that I basically need. Next, each gate, if I draw a gate here, the circle is missing here, if I draw a C0, for example, here, this control part and the target part must be encoded as a subroutine. Because this logical gate, logical qubit, is implemented by many physical qubits, I must implement this part of the gate also as a subroutine here and this part as a subroutine here. So the gates become more complicated. And I must run, after 1, 2, 3 steps that I perform, these error correcting steps on these bundles of logical qubits. Right? That means it becomes much more complicated. I need many more qubits, physical qubits, to realize error-free qubits, and I need subroutines that consist out of several gates in order to realize error-corrected gates. Right? So this is the implication of noise. N noisy physical bits are needed to realize one stable logical bit. More qubits are needed. And a single universal but noisy gate is realized by a quantum subroutine. And error correction must be run periodically. That means more operations are needed than estimated by a theoretician. Right? That means we are in the NISQ era. Again, you and I have written a paper about error code, error correction, what problems appear in the NISQ world, and so on. Right? So technological problems is, I mentioned before, decoherence, the state of qubit decay, and I mentioned the goose, right? Gate fidelity, you can't rotate around an arbitrary angle without errors. Readout, very interesting. If you want to read information out of a quantum computer, it takes typically longer than running the complete algorithm. So reading out information is more complicated than computing itself, right? Interesting. That means I need more readout creates errors, and this is based on this qubit connectivity I mentioned. If you want to have a 2-qubit gate between 2 qubits, they must be connected on the machine, on the chip. Otherwise, you need to have swap operations and swap them to a situation where you can entangle them. We discussed decoherence. Here, a figure there. We distinguish 2 different errors: relaxation time, where the state of 1 qubit goes into the diagonal state here, or whether the qubit is just fiddling around, which is called the dephasing time. Right? And machine vendors basically report their relaxation time as well as dephasing time. Dephasing time is very short. It happens very often that the qubit is fiddling around. Gate infidelity, we said that because gates are rotations. Readout errors, I also mentioned readout errors in the meantime. I'll skip over that in the interest of time. And implication of readout errors is also you need to increase your circuits in order to protect yourself from readout errors. So, how do you get data into a quantum computer? So we discussed now unitary transformation. We had 2 examples of algorithms, the Deutsch-Joscha algorithm, the Shor algorithm. Now we are discussing, we abstractly understood that classical data must be transformed into quantum states. Now we're discussing how this works, for example. Right? There are various kinds of, we call it data preparation mechanisms. Right? There is something called base encoding, amplitude encoding, tensor product encoding. I will mention that. Right? For example, base encoding lets you transform natural numbers into a quantum state. The natural number will be represented in binary code as a series of bits, right? And the base encoding basically takes the bits, the natural number is rewritten in as the ground states 0 or 1 of the quantum register, right? This is called one of the digital encodings. There are several digital encodings. This is a very simple one because other ones are more complicated, right? You can pump very easy a natural number to a quantum computer, for example, to do prime factorization. This is the circuit. You are not really interested in how the circuits look like. And An individual qubit can also be prepared based on this a spherical coordinate representation that I mentioned at the very beginning, right? This is the matrix that you use, a unitary matrix, to prepare this particular state in your quantum computer. And you can realize it by these 3 rotations here, right? So an individual qubit can immediately map very fast to a quantum computer. You can prepare a whole quantum register by something that is called Schmidt decomposition. You may have heard that in linear algebra, right? Schmidt decomposition of a matrix basically allows you to rewrite it based on unitary and Hermitian matrices. And if you have a very complicated state, you compute its Schmidt decomposition classically. You compute this kind of matrices, A, U, and V. These are matrices that mathematics tell you how to compute them. You represent them as quantum circuits, quantum circuit U, V, V, and then you have a very complicated state pumped into the quantum computer. But the implication always is data preparation requires additional operations to transform the classical data into quantum data. And oracles. We mentioned a couple of times subroutines. If you read a quantum physics paper claiming that the author has a very new fancy algorithm, they most often have, there's an oracle. And they say, okay, I invoke the oracle only once. This is a very slim algorithm, but don't believe the quantum physicists. I hope not too many quantum physicists are here. Because this is complicated to implement. They compute the complexity of their algorithms in terms of complexity of one of this. So one invocation of a subroutine adds 1, the number 1, to the complexity of the algorithm, which is a lie, because these oracles look differently. Here we had this, the Deutsch-Joscha algorithm that compute, here's for example the function, this is a balanced function, 50% of the values are mapped to 1, 50% mapped to 0, and I need to build an oracle function that implements exactly this map F here. And my claim is that this little quantum circuit, which is equivalent to this function. So if I have a hollow circle here, the hollow circle is the control knot that is controlled by 0, not by 1. So controlled by 0 means only if it's 0, this is negated. And how can I realize this gate? Well, I add an X gate here, because if this is 0, I added this is a 0, and so on. So this circuit is this circuit, but the whole message is an oracle in a circuit must always be substituted by a subcircuit, which increases the depth, sometimes the breadth, yeah, and so on. You need also take a look there. And here, by the way, is an implementation of the Deutsch-Joscha algorithm on a real quantum computer. I'll skip over it. So the implication of oracles is you require additional operations compared to an ideal operation, because quantum physicists count oracles as a single gate. In fact, it's a bunch of gates. It's a whole subroutine. We, as computer scientists, need to analyze it, right? And we have this NISQ analyzer that I briefly mentioned that does it for you. So NISQ is the attempt to do meaningful quantum computing in a noisy environment. That means you have only a few hundred qubits available, limited number of operations to provide, to prove quantum supremacy. But the problem is dequantization. Dequantization is the problem that not only classical computers become more and more powerful, right? But the problem is as follows. In the last couple of years, the classical computer scientists became absolutely jealous because of the quantum computer scientists inventing algorithms that are exponentially faster than the classical ones. And the classical computer scientists said, gee, I proved that I'm smarter than you. And they develop at the sudden algorithms that are also classically polynomial. So we are in a period of a couple of years where we see formally exponential algorithms substituted by polynomial classical algorithms. This is called dequantization. So the quantum computing guys now become angry because if they publish an algorithm, tons of classical computer scientists jump onto the algorithm and prove, I have a classical algorithm that is as good as yours. We don't need these crappy quantum computers. This is dequantization that's currently happening. So some problems that couldn't be solved classically in the past can in the meantime be solved polynomial because of this race between quantum computing guys and classical computing guys. But the noisy machines, as I said before, they need the algorithm run only for a short period of time. And what people invented is called a variational quantum algorithm. A variational algorithm is an algorithm that has a quantum part that has a bunch of parameters here, typically angles that are used to rotate individual qubits around. Then I perform a measurement, get the measurement result out, and this measurement result is analyzed, optimized, to produce new parameters, and the new parameters are fed to this quantum part, and then I have a loop here, and when the optimization succeeds, I found my result. And the goal of a variational quantum algorithm is that the time I need to perform my quantum part plus the time I need to measure on the quantum computer is significantly smaller than the decoherence time, because then I'm protected by errors. If I'm very fast on my quantum computer, before decoherence happens, there are no errors. So the quantum part is this kind is suitable for today's NISQ machines. Sample VQAs, there are many variational quantum algorithms. I only want to mention the variational quantum eigensolver. It can compute eigen values as well as eigen vectors. Right? This algorithm has an exponential speed up compared to classical algorithms, and it can be used in many situations. For example, max-cut can be solved, maximum cut algorithm, which in turn is used in clustering, classification algorithms, and so on. And the so-called QAWA algorithm, meaning quantum approximate optimization algorithm, algorithms that can solve combinatorial optimization problems. They are often, not always, faster than the best known classical algorithm. That means we need to understand the problem structure before we can say that the quantum computer can this kind of problem solve faster than the classical computer. This is also work that we as computer scientists need to work on. It looks terrible, complicated. This is the so-called QAWA algorithm. In fact, it's easily to implement, and it requires here an optimizer. You have parameters. You optimize the angles gamma and beta. You optimize them. When the optimization criteria is met, then you solve the problem, basically. VQE is this algorithm. Again, here you have a classical part. The classical optimizer is optimizing some parameters, right? And that basically means this is a hybrid algorithm. You have parts on your QPU. You have parts on the CPU. Typically, it's optimization problem. You use an optimizer on the cost function. The problem, the real challenge here is to find a cost function that represents the problem you want to solve. It's an art, right? You understand the problem, and then you need to invent a cost function that represents the structure of your problem, and then you run this variational loop here to solve the problem. And this can be rewritten. Some of you know BPMN. It's a workflow language. I can represent this workflow, this loop in a workflow. I start here with an exclusive gate. I execute my Ansatz. The quantum algorithm is called the Ansatz. It's a German word for my attempt. I attempt to solve the problem with the circuit. You execute the Ansatz. You evaluate classically. The hammer represents classical. The atom represents the quantum part. I evaluate classically the cost function with an optimizer. I determine whether the optimizer says, yet I reach the optimum. If not, I go here, and so on. I perform this loop. So today's algorithms are also all hybrid, based on optimizers that I used. But this is trivial. This is a very trivial process here. In fact, you need a much more complicated process, because this is from a paper that Johanna did published, and she will refine something like that later on. You need to retrieve data. And all machine learning algorithm, or most machine learning algorithms, do assume that the data is numerical data, points in the vector space. But in fact, many, many data are textual, some customer data and so on. So you need to transform text information into numerical data, right? And these are steps that you can perform in a data preparation step here, data preparation step. Textual data is transformed into numerical data. Then you do feature engineering, right? You need to determine the features. How do you do that? Based on principal component analysis. Principal component analysis requires the determination of eigenvalues. And here we have a quantum part. We use VQE in order to determine eigenvalues. In order to do so, we must transform this numerical data into a representation of Pauli matrices, right? Once we have performed the principal component analysis, we want to use Quawa to compute the cluster. Quawa can solve the max-cut problem. Max-cut is underlying also for computing clusters of data. So here we come now in the clustering part. We compute something, a certain kind of graph. We transform it into a Hamiltonian cost operator, blah, blah, blah. We don't understand the details. And then you have a sub-process that is using a quantum computer to compute the clusters, right? So this is an absolute real-world process. What it basically means, and you involve this process, if this is some sort of BPMN diagram, right, these abstract steps are implemented by classical code, for example. That basically means the retrieved data step in this real-world workflow needs to invoke a piece of code, Java code. This compute distance matrix may invoke an API that is the API of a cell. My WSO2 colleagues know that. Within the cell, I have microservices that are integrated with a micro integrator and computes then the result of the distance matrix. So what that means is you need to describe the dependencies of the code that the workflow engine should invoke. The retrieve data is a Java program that runs in a JVM, that runs on a server machine. The data is in fact a customer database under DB2, forgive my IBM heritage, that requires a Linux operating system that runs in a virtual machine, and the retrieved data piece of code is connected to a customer. This kind of diagram is called a topology diagram in cloud computing, right? So what you really need is you need to package all of this together in something we call a quantum application archive. All the artifacts are in an archive that you can deploy in a cloud environment later on, right? So what you need in order to build today's application is you have a workflow, you need a workflow engine that executes the workflow, and whenever the workflow engine determines that it needs to invoke a piece of code, it needs a provisioning engine to deploy the piece of code that needs to be executed. Here's another paper that we have written on this subject here. So you require two orchestration, workflow orchestration, topology orchestration in, this is a joke, in a superposition, right? They need to be superimposed. At the tooling level, you need an API manager for this kind of hybrid quantum application. You need to model the dependencies of code, topology model, and an engine that understands it and runs it. You need a workflow modeling tool and a workflow engine that interprets the models here. This is what we all need. And promising applications that we have implemented is machine learning, recommender stuff, simulation, and so on. And we are, sorry for the German, this is a German acronym here, a project called Planck. This is the acronym. You won't understand it even if I read it in German. And we built a platform here that is available. You can get a user ID. It's planck.de. You go there, get a user ID, then you have a whole platform available. The platform does as follows. The platform has a crawler that inspects quantum papers and analyzes the and downloads the quantum papers into a content data store. Then we had a bunch of quantum physicists who analyzed the papers, whether the author was a little bit cheating or whether the algorithm is really beneficial. And we store this into a quantum algorithm. So sanitized papers are stored here. Then we had developers that basically analyzed the algorithm and detected something that we call a pattern. In computer science, a pattern is a proven solution to a recurring problem, right? And these patterns have then been implemented as pieces of code, right? In classical code, quantum code, everything is accessible via an API, right? We have tooling, we have a NISQ analyzer. The NISQ analyzer has access to existing, this figure doesn't show it, to existing hardware, INQ, AQT, IBM, Rigetti, and it basically periodically goes to the hardware and determines the actual state. What is the decoherence time of the chips? What is the error rate of the gates? And then based on this information, the provenance information, this component analyzes on which machine the algorithm may be able to run now, right? Because the machines need to be reset every couple of hours. Right? Then we had a workflow engine not shown here, and this overall environment is then something that has been used by industry partners to implement real-world applications. And these real-world applications are also available on this platform, so you can take a look at the real-world application, what has been implemented there, and how to use the different tools. So, and last focus was on machine learning, clustering, classification, optimization, this gate assignment that I mentioned, right? It is also used on a small scale to optimize power networks. So a lot of application areas that you will find there. And Johanna will show you now, and Kazoo needs to tell me whether we should have a break or not. No break, no break. Oh, the people are, okay. So he is guilty. He is guilty. So Johanna will speak now for 30, 35 minutes on applying quantum computing in the humanities. Not only in engineering stuff, but she's working on humanities. Johanna. By the way, while Johanna sets up machine, here are papers that Johanna has written on how to use quantum computing in the humanities. Say again?
I'm on researchgate.net. Do you have papers on ResearchGate?
On archive.
ResearchGate, there's a site called ResearchGate where they have researchers do that.
Yeah, I'm lazy in publishing ResearchGate. I publish in archive and on my website, right? And sometimes I get inquiries. I think I have 10,000 open inquiries. No, I don't use ResearchGate. But it's on archive. If you go in archive, type my or her name, then we'll find papers in this domain. If you're not, send me a mail or send it to Kazoo if you know Kazoo, and I will send you a list of papers. Yeah? Welcome.
So for the last half an hour, which is not too long to go anymore, so soon you made it, I will talk a little bit about one of the tools we did design and implement at our institute. There are quite a bunch of tools we implemented in the area of quantum computing, but this one is a tool for comparing classical and quantum machine learning algorithms. And it's called QANA, which comes from Quantum Humanities Analysis Tool. And you should not worry about the quantum humanities too much. This is where we started off with. But it's actually a tool you can use for various different use cases from different areas to analyze data. But as it started off with the quantum humanities, and just to give you some insights on what we're doing there, I want to start to give a quick introduction what we do mean with quantum humanities and about our first use case, as we can show what the tool can do very nicely on this use case. So what are quantum humanities? There are two starting points we need to consider. The first one is, and we've seen this in Frank's talk now very nicely already, he gave us a broad overview. Quantum computer has become some sort of reality during the last years. So in industry, we have a lot of applications in product and material simulation, in optimization, in security. We've heard about that now in the talk before already. In natural science, we have some applications too already. We use it for molecule simulation in material science or in machine learning, as we've heard, or in optimization. And there are quite a few uses already. but when it comes to the humanities, they're always a bit behind, they're always a bit slower. There's nothing yet. On the other hand, and this is the second starting point, we got an establishment of the digital humanities, how they call it. So that means a lot of new approaches have been developed to solve existing, but also new questions from the humanities by using the ways of thinking, by using tools from the computer science area. This is what digital humanities mean. So nowadays, they only use the classical computer. So it's quite easy to ask, why not using the potential quantum computers can offer us too? And as we have seen, it's quite complicated to work with quantum computers, so we need some tools and some mechanisms to make this possible for humanities to be used too. Why should we use the quantum computer? This is just one slide summing up a lot of things we've heard in Frank's talk. And I do admit it's a bit simplified, but when it comes to an ideal quantum computer, and we have heard we are not there yet, we're still in the NISQ area. But if it comes to an ideal quantum computer, these are the 7 points we need to keep in mind why we are interested in working with quantum computers. So first of all, what we heard right at the beginning of Frank's talk, they can solve certain type of problems much faster than a classical computer, point 1. The second one is they enable processing a large amount of data in just a single step. Think about the quantum parallelism we've learned from before. The third one is the results promise to be of a higher degree of accuracy, which is really, really important in the area of machine learning. And we will come to this later on when we go make the deep dive into the tool. Next point is they solve problem classes which are practically not solvable so far. Coming again to molecule simulation. Here we have a lot of potential. The next one is we've heard by Frank in Frank's talk already, there are some problems we can only really address with a quantum computer. So there's a lot of potential we need to look at if there's some application for the area of humanities too. The last 2 points are a bit more on the practical side, so they promise to be quite cheap. So if you look at how much money you need to pay to go to a supercomputer, it very easily gets really, really, really expensive. So if this is something that gives us access to a lot of computing power for less money, and a lot of humanity research projects have no money at all, this is something we should think about it. And the last one we hadn't talked about at all yet, they're incredible energy efficient. So even if all the other points don't hold and we are living in times of climate change, at least this is probably something we should think about and we should get involved with. So this is if we get really good ideal quantum computers we want to participate in. This is not where we are now, but still we need now to get to know this algorithm, to get to know how to work with them so that if they're ready, we are ready too. So coming to quantum humanities again, when you look at how humanities research is done from the ancient years, so they have a very long tradition, the hermeneutic is the method they are using. So they're looking at certain artifacts, like a book, for example, and they're trying to analyze them, they're trying to describe them, they're trying to find an explanation about these artifacts. I have some troubles with my pointer. So, with digital humanities, I said before, we can now not only just analyze one book, but due to all those different tools and methods and ways of thinking, like semantics, visualization, distant reading, and so on, we can ask much bigger questions for a whole pile of books. And with the quantum computing, we have now seen in Frank's talk that there's a lot of potential coming true. So I tried to show it by showing a whole library. We can ask much bigger questions again. But they're very different in the handling, very different in a way of thinking to get an algorithm running, to get them really working. This is why we coined this new term, quantum humanities, for this kind of area of research. So coming to our first use case, our first feasibility study in the area of quantum humanities. This is a project running for quite a while, already more than 10 years now. And it's a project where we are looking at costume languages in films. So something very, very different. But this is where we got a lot of data And this was our first use case to try to compare quantum and classical algorithms to analyze the data. And if you've ever done a machine learning project, you will know that the key part is knowing your data to get some really good results. So I will make a quick introduction how we got this data and then show you how you can use it in Kyana. So I said it's about costume language. Costume language is something based on vestimentary communication, something we use in our everyday world, because look at the people next to you, most of them are dressed. So what we see of the other people is 80% clothes. And in films, we have this situation where a costume designer is there who picks every piece we see, the material, the color, the shape, and so on a certain purpose, to give an impression, to get a certain effect. So the idea of the project at the beginning was, we want to extract this costume language by looking at a lot of different movies, getting the data out of this movie. This is what we did with our Muse tool chain. And we want to find out which elements are significant to, for example, here we have the example of a sheriff. So we look at a lot of sheriff's costumes to see what are the significant elements you do need to communicate a sheriff. You need a hat, you need a star, you need the boots, and so on. And therefore, we had a 5-step approach we did follow. So first of all, we started off with defining the domain, meaning building a huge ontology that helped us to describe each costume in detail. So which values are there in color and material and so on. The second step was, of course, we needed to make a decision which movies we want to look at. The third step was we did create our Muse repository where all the data are captured in a structured way. Then we needed to analyze this data, of course. And this is what we will see later on in a bit more detail in our Kyana use case. And then we want to interpret the elements that are significant as costume patterns. And costume patterns can be something like a sheriff, but it also can be if you roll up your sleeve, you look more active, or blue is more used for more calm characters, and so on. So coming now a bit more close to this performing analysis part, because this is where our quantum computer comes in now. Again, we had now the Muse database where all the data are stored in. So we got a lot of data. We need to extract a feature so we can put all the data, these are our spots in the feature space, can be mapped in a feature space. We then want to do some clustering to group those costumes together. You can see this a little bit with the colors. It shows the clusters. We want to group those costumes together who have the same effect. For example, putting all the sheriff costumes in one cluster. And we want to perform a classification. This step is to find the perfect hyperplanes that separate our clusters we have identified in the steps before, so that if we have a new costume that gets stored in our database again, we want for sure know immediately, as it is part of the red dots, sorry, that it is a sheriff costume. So this was the first starting of idea. And now we can do this with a lot of different algorithms, with a lot of different approaches. And there are classical ones, but of course there are also some quantum ways of doing this nowadays already. So we wanted to find out which of the quantum algorithms are actually there already and how good are they really. Do they work? Can we use them? So when you do data analysis, it's not just running an algorithm. It has a lot of different steps. So this is just one very classical overall data analysis pipeline you can see here. And it looks very nicely straightforward. It's never like this if you have a machine learning project, because normally you prepare your data, you run your algorithm, you want to build a hypothesis. It doesn't work, so you have to go back to a different one. And of course, this needs to be specified for the specific use case at hand you have got. But going through the steps a bit more in detail, so data cleansing does include getting together all your data. It includes looking if the formats are fitting to each other, how do you treat missing values, how to repair the data if they are not perfectly yet. Data preparation, here it gets a bit more tricky. you have very often, Frank said so already, the problem that you are coping with categorical data in real-world applications. So most of the algorithms need numerical data. You need to somehow transform them. You need to think about which encoding you want to use, like a one-hot encoding. You need to think about how to engineer your features. Do you want to do a feature selection or feature extraction? Or maybe you want to reduce the dimension. So there are a lot of questions right before you even have started with the actual algorithm. Also, selecting the algorithm is not that easy, as there are bunches of algorithms out there. The first thing is to select the family of the algorithm. So what do you actually really want to do? You want to do a classification, a clustering, a regression, and so on. If you have decided on the family, you need to select the actual member of the family. So if you do a clustering, maybe you want to use an optics, an k-means, max-cut, and so on. You then need to decide on the hyperparameters, so on the settings of your algorithm, and then you can execute it. Next step is you get some results. You need to evaluate them. So hopefully you get a good visualization that allows you to build a hypothesis. Very often that doesn't work, as I said before, so you have to go back again. If you're lucky, you can build a hypothesis, and of course this needs some validation. So based on this overall data analysis pipeline, we chose the steps we needed for our project. As I said before, we wanted to do clustering classification. Before that, we needed some feature engineering and some data preparation, and that's what Kyana now supports. So we're coming now to the tool, actually. We can see here the main menu of Kyana. So it does support exactly the steps we saw before. And as I said, so you can do this in many, many different ways. There are different algorithms, there are different implementations of the algorithms, there are different hyperparameters of the algorithms, so you need to try it out a little. And then it comes to, there are also max-cut classical and quantum-based, so there's a lot of things you can test and try out. So we go now through this a little bit more in detail, starting off with the data preparation step, and I will start with the distance-based computation step, what we are using. As I said before, we have the problem with the categorical data that needs to be mapped into numerical data. What we are doing is we are using the structure of our data to transform it in numerical data. So this is German, I know, but I will explain to you what I mean. This is a very tiny picture of our ontology. You can see the total ontology has more than 3,000 different items. And this is to describe each costume in detail. So it has a base element, which is a dress, some shoes, and so on. Each base element has primitives. And behind each of those different attributes, there is another taxonomy. So it has primitives, it has shapes, material, colors. And so I can describe my dress very nicely. It's a half-short dress. It has got no sleeves, no color, and so on, to make it very in detail captured in the repository. So it gets a bit more complicated, as my outfit has only shoes and a dress, but sometimes you have got much more items, so you need some operators that make a whole outfit. So it has some operators too. And this data is quite complex to analyze, but this taxonomy gives us a very good structure that allows us to map the data, we've got the category data, to similarity measures. So I can use now this taxonomy. We can see here the colors, the taxonomy of the colors. I've got all the different colors we used in our tool. And based on the Wu and Palmer metric, which is the formula down here, I can give every item in my taxonomy a similarity measure to another one. So putting them into the formula, I get just one similarity measure for my blue and red dot. And they very nicely reflect that a light yellow and a blue yellow are not close at all, but a light yellow and a dark yellow are very close to each other. So they reflect the information that is stored in our taxonomy, and that helps us to transform the categorical to a numerical data. It's a bit more complex, as each costume does not only have one color. We have here, down there, we've got costume A and costume B. And costume A, for example, has different colors and different materials and different designs. And I need to calculate all the different similarity measures. I need to build the mean again. And then I need to build the mean between the color and the material and so on to get one final similarity measure that allows me to say this costume is that similar to another costume. And I have represented all this information in this numerical data. So this is where Kyana helps you. I can go to a distance-based computation. I can choose the different parameters I want to look at. I can choose how the similarities should be measured. I can transform them very easily in distant measurements. So I get a distant matrix like this, for example. I have 25 costumes here comparing color and the genre. And I've got down here the blue ones is if they are similar to each other. The red one up there is there's no similarity at all, so 1. And we can see here right in the middle that each costume is, of course, similar to to itself. But if you look at the 1, it's really bad that my pointer doesn't work. If you go with the 1 to maybe the 10, you can see that they are quite similar. If you go to the 11, there's no similarity at all anymore. So this is one way of doing it, to make this data preparation step at the beginning. I said Kyana is about comparing ways. So we can do this using a quantum computer too. So here's another way, a more statistical way we can do it. We can use an autoencoder. The principal structure is shown here, so it's a very abstracted way. It's a neural net, actually. We got an encoder part and a decoder part, and the encoder has an input layer where all our data comes in, and the code part at the middle is a reduced representation of the information we stored, and the decoder tries to reconstruct our input parameters again based on the code, so based on the reduced representation. And this is something we can do on a quantum computer already. So it's not very good to see, it's just to give you an impression. We have a 4-qubit circuit here. We got our input preparation at the beginning, then we got the encoder part with a lot of gates. We then reset, oh, it's really hard to see, I hope. We reset 2 of the qubits to 0. So all the information is actually stored in just 2 qubits anymore. And then the decoder tries, based on the information that is in these 2 qubits, to reconstruct again our input parameter out here, and then we do some measurement. So we have now the result of a distant matrix of 10 costumes again, and we have on this side the result of the hybrid autoencoder using the quantum computer, and we have got on this side the results we got using the Wu-Palmer metric, so using the taxonomies. And we can see quite nicely that up here, the first 5 costumes are quite similar to each other. The others are not. And we got a very similar result, actually, by using a totally different way. So this is getting a first feeling. We can use either this one or the other one. It gets a bit more interesting when we come to the next algorithms. We have now numerical data. We can put this numerical data based on a multi-dimensional scaling, for example, into a 2-dimensional space, and I can run now some cluster algorithm on it. Here we can see just a few cluster algorithms that are part of the tools, and down here I can see if I chose the Quora max-cut, so a quantum-based max-cut algorithm, I see the hyperparameters. I can also choose on which backend they should be run, as it has a big impact on the result, which backends I am using. And so I can try to cluster this data now. We got here now the results, first of all, after the multi-dimensional scaling. So we got it in a 2-dimensional space, again, the 10 costumes we saw before. And we do expect on this side, as there are a few data spots, one cluster, we do expect another cluster on the other side, as it is very simple data. We see down here the results of a classical max cut, and we see down up there the results of a COA max cut. So if you look at the twos down here, you can see they do exactly what we expect. Very nice. This is not very nice. So we're not really happy with the result of the quantum algorithm. So what you can do in Kyana now, going back to the hyperparameters, fiddling around with the hyperparameter, so going back again to find some other hyperparameters, maybe you can learn a little bit how to do the settings of the algorithm to improve the results. So what we did is we increased the number of iterations running. And here we've got the result of the maximum of the max cut quantum based, where we increased the number of iterations performed from 1 to 50 to 100 to 150. And we can see quite nicely that it got better each time. This is really bad. A little bit better as we got already 3 of the dots clustered right. It's not too good, but we needed really the 150 iterations to make it as good as the classical ones. So maybe this is not the best way of doing the clustering. But we learned a lot about the algorithm, how to set it. So if you have a bigger data set, we can use this configuration. We know now already how to configure the algorithm to get good results. We can do this with more data points. This is just to show that it's not only 10 costumes, but here we did it with 40 costumes. It's a classical quantum, classical k-means and a quantum k-means, and they actually did both perform very well. They did what we wanted. We can now, as I said, we want to find the hyperplanes in between. We can now do some classification step, and here we see a few of the different classifications that are available there. And here we have a support vector machine. We use the support vector machine based on a quantum kernel in this experiment. And we got here the result. On this part, classical support vector machine. On this part, the quantum kernel estimation. And what we have got, we got the labeled data. So after the clustering, we got labeled data. We got the purple points labeled negative, the blue points labeled positive. And as I said, we want to find the hyperplane that allows us that all the yellow, and, all the purple and the red dots are just on one side. The number that is interesting for us is actually the accuracy up there. So here we can see that only 72% of the data are labeled right. If you come to the quantum support vector machine, we can see that we reached an accuracy of 90%, which is much higher than this. So other than with the clustering algorithm, the classification worked really, really good. Of course, we need to go back. We need to be fair. We went back with the clustering, so we need to do this here. We tried it again with different kernel functions. We also fiddled around with the hyperparameters of the kernel function. We got worse. We got better. So 81% was much better, but we never reached the 90%. So this is already giving you a hint that this getting more precise results by using a quantum kernel machine is really of interest. Maybe not for the costumes, but it will be of interest when you look at the other publications that have been there last half a year on breast cancering data, on financial data. A little bit of more precision in this area is a lot we gained. So these are the experiments you can do. Summing so up a little bit what Kyana actually has been designed for and what we're using it for. It's to make an easy comparison of classical and quantum-based analysis algorithm, therefore. And it's a lot about trying to find the right hyperparameter. How does different QPUs react? Which ones are good? Which ones are bad? It's to provide a very easy access for people who are not that deeply involved in mathematics and physics. It's to get all those different heterogeneous tools in just a single pipeline. And we come to this now. It's not only for the costumes. We started off with the costumes, but it's actually independent of the presented use case. So what we did is a total re-engineering again. So we wanted to make Kyana fit for individual workflow support. So maybe you've got you got some data, you want to analyze the data, and your workflow looks like this. You want to retrieve data, reduce the features, label the data, train a neural net. And again, first of all, you want Kyana to support it, and of course, again, there are a lot of different ways of doing it. So what we did, this slide was shown by Frank already. We want that based on your individual workflow, that you can get the different algorithms that are there, invoke them by an API, and let them run. So our new Kyana architecture, very simple, the 3-component architecture. We got a new Kyana UI that actually allows you to define your experiments, to run your experiments for your special use case. They are stored in the backend, and the heart actually is our plugin runner. This is where you design all the algorithms. They are wrapped as plugins that have the actual algorithm, an API, and a micro front end. And it looks like this now. So here you've got all the different plugins that allow you to put together the individual workflow you need for your for the analysis of your data. You can choose, and based on the micro front ends, you're allowed to still select the hyperparameters and so on. So translating the Muse use case we have seen in the new plugin-based architecture, we need a plugin for loading the data. We need some plugins for doing the data preparation I showed based on the Wien-Palmer metric. So these are all the different plugins I do need for this step. I then have my quantum part where, for example, the quantum k-means is running, and I have a visualization again at the end. If you don't want to design your own one, you can use templates that have already worked very well in other use cases. You can use the Muse template. These are the plugins I just showed. If this is close to what you want to do with your data. We have another project running which is in the area of musicology, which is called Music for Music. So there we are looking at which parameters in music are used to communicate horror or communicate joy and so on. So we're making analysis of scores. And as this data looks quite similar to our data, they can just use the Muse template and do their analysis very easily there too. You can then let your experiment run, and at the end, of course, you get, like in the old Kyana, the visualization you can compare and get a feeling of your algorithms. So Kyana is, I said, a tool we did in our research lab in Stuttgart. So it's a research prototype. Of course, there are some plugins missing, and not all of the algorithms are rendered properly as APIs yet, but still, it's open source, it's out there, you can use it. If you have some data you want to analyze, there is a user guide, and there you can find all the different GitHub links to the repositories. And also there's a quite good documentation where you can just go through a tutorial to learn about it. So if you're interested, go there, try, and get some first quantum algorithms running for yourself. So this was half an hour running through, and I will give back to you on the final 9.
So, no summary slide. I try to wrap up what we did today. So we began with a very, very brief overview what the main aspects of quantum physics basically, or quantum mechanics basically are. We then discussed what the hell is a qubit? What does the power of qubit come from? Right, it's superposition of 0 and true. It has an infinite number of potential values. We created entanglement as a mechanism that allows you to do things that you cannot do classically at all. We found out that manipulation of a qubit is a unitary linear map, a unitary map. We found out that manipulating a quantum register that introduced quantum parallelism is another unitary map, and that unitary maps can be represented by 1-qubit operators and the C0 operator. We discussed what a quantum circuit is in principle, took a look at some tools that you use in order to define quantum circuits. Next, we moved over and took a look at the Deutsch-Joscha algorithm, which was an algorithm that showed the first ever exponential speed up compared to a classical algorithm, analyzed that and found out that quantum computers especially can be used to analyze global properties of function. Then we took a look at we took a look at prime factorization and also saw the prime factorization is all about finding global properties of a certain function, namely the periodicity of the module exponential function. Showed that periods can be determined based on Fourier analysis, and there is an algorithm for quantum Fourier analysis. And once we determined the periods, we could crack keys, but we can also compute discrete logarithms, which is at the heart of elliptic curve cryptography. We analyzed we analyzed errors in quantum computer, namely decoherency and lack of fidelity of quantum operations. We took a very brief look to quantum error correction in order to get rid of noisy machines, in order to get stable machines. And we basically mentioned what logical versus physical qubits are, that you need subroutines that implement gates on these logical qubits. And we also mentioned that even today you can run useful algorithms based on variational quantum algorithms. Variational quantum algorithms are under the premise that you need to spend as few time as possible on a quantum computer. That means you prepare some state, you measure the outcome, and then you have a problem-specific cost function that tries to optimize the parameters of the parameterized circuit. I very briefly mentioned VQE, a variational quantum algorithm to compute eigenvalues, and Quawa that can be used to optimize combinatorial optimization, to solve combinatorial optimization problems. Said that all these algorithms, even classical algorithms, are hybrid. You always need classical computer in concert with the quantum computer. We mapped that at the sudden to a workflow to show that this hybrid loop quantum optimizer is in fact a workflow. We gave you a more complicated workflow from a real world use case that you need workflow technology in order to describe your overall application. And then Johanna gave you also a brief look on a tool that you can use to play around with classical algorithms and quantum algorithms to find out whether, based on your problems, even today, quantum algorithms may be useful. This was a very huge, we covered a lot this afternoon. I hope you had a halfway pleasant stay, right? It was a lot of material. We will make the slides available for those of you who would like to see them, right? And we are also discussing possibilities maybe to come back in autumn and give a more lengthy tutorial, maybe even a lecture on quantum computing with exercises if you are interested in it. This covers the day. If you have questions, right, feel free to send them to me. I hope I find time and respond. So if there are not too many questions, I will respond. Otherwise, I wish you now a very nice Sunday. Enjoy the day a little bit, and I wish you a lot of success in your studies here at the University of Colombo. Right? Have a good time.
That concludes this interesting sessions. I would like to thank you again for Professor Frank and Johanna on delivering this very, very interesting talk. They take us from deep mathematics to the practical applications. That's open up, I believe, very interesting new areas where you should study and focus and do research and so on. So it's They are very kind, frank. They agree to come back and give deep talks on maths and quantum computing somewhere down the line of the year. So by hoping we will meet back again, thank you very much for participating. Have a pleasant evening. Thank you.